Hello there, and welcome to Physics with William, where science is allowed to slow down, take a comfortable seat, and explain itself without rushing towards the next idea. Tonight, we are looking at an atom that sounds as though it should not be able to exist. It is called muonium, and it is made from one particle of ordinary matter and one particle of antimatter. That description is enough to make the imagination hurry ahead. Matter and antimatter are famous for destroying each other when they meet, releasing their stored energy in a sudden burst. So an atom that contains both may sound less like a stable object and more like a very small argument waiting to become an explosion. Yet muonium really does form. It can behave like an atom. It can move through materials. It can absorb energy in precise amounts. Scientists can study its internal behavior with lasers, microwaves, magnetic fields, and carefully timed detectors. It does not last long. Muonium usually exists for only a few millionths of a second because one of its ingredients is naturally unstable. That may seem far too brief to investigate, especially when most of us can lose several minutes simply deciding whether to get out of bed. For particle physicists, however, a few millionths of a second can be a generous window. Modern instruments can produce large numbers of these atoms, watch what happens to them, and combine many short observations into measurements of remarkable precision. Before we go further, where are you listening from tonight? Are you somewhere quiet with the lights low and the day nearly finished? Or are you listening in the middle of an afternoon that still has several tasks left in it? You may also tell me what first brought you to the subject. Perhaps you already know what a muon is. Perhaps the word muonium appeared somewhere and sounded like a fictional metal from an old science fiction film. Or perhaps you saw the phrase atom made of matter and antimatter and reasonably wondered how the atom survives long enough to deserve a name. If you find this kind of calm scientific wandering useful, you can leave a like and subscribe to the channel. It helps other curious people find this quiet corner of physics, including those who enjoy learning about the universe, while trying not to become more awake than they were 5 minutes ago. The first thing to understand is that muonium is not an element in the ordinary chemical sense. You will not find a piece of muonium in a mineral cabinet. There is no bottle of it waiting on a laboratory shelf, and no one is likely to build a kitchen worktop from it. It is an exotic atom, which means that it has the basic arrangement of an atom but uses at least one unusual particle in place of the familiar parts. A normal hydrogen atom provides the easiest comparison. Hydrogen contains a proton with a positive electric charge and an electron with a negative electric charge. Opposite charges attract, so the electron becomes bound to the proton. Quantum mechanics does not describe the electron as a tiny planet following a neat circular path. Instead, it gives us a spread of possible locations and energy states around the central positive particle. Even so, the simple picture of one negative particle held near one positive particle is a useful place to begin. Muonium has almost the same electrical arrangement. It contains an electron with a negative charge. At the centre is a positive muon, also called an antimuon. The positive muon attracts the electron, and the pair forms a neutral bound system. From the outside, muonium resembles an extremely light version of hydrogen. It has no overall electric charge, and its electron responds to electromagnetic forces in ways that allow the system to display familiar atomic behavior. The surprising word in that description is antimuon. A positive muon is the antimatter partner of the negative muon. The negative muon belongs to the matter side of the particle family, while the positive muon belongs to the antimatter side. The electron in muonium is an ordinary matter particle. This means the atom truly does contain matter and antimatter at the same time. Why do they not immediately annihilate? The answer is that annihilation is not a general rule, saying that any piece of matter destroys any piece of antimatter. A particle can directly annihilate with its own antiparticle. An electron can annihilate with a positron, because the positron is the electron's antimatter partner. A negative muon can annihilate with a positive muon because they are partners of the same type. But an electron, and a positive muon are different kinds of particles. They belong to the same broad group called leptons, but they are not each other's particle and antiparticle pair. A house cat and a tiger are both cats, but they are not interchangeable. The comparison becomes unreliable if we push it too far, as most comparisons involving tigers eventually do, but it captures the basic point. The electron and the positive muon are related members of a larger family. They carry opposite electric charges, so they attract. They do not match in the specific way required for direct mutual annihilation. That distinction allows muonium to form instead of vanishing at the instant of contact. The electron remains bound by the electromagnetic attraction between opposite charges. The positive muon sits in the position normally occupied by the proton in hydrogen. Calling it the center does not mean it stays perfectly still. Both particles move according to quantum rules, but the muon is much heavier than the electron, so the simpler picture places the heavier particle near the middle and the lighter electron around it. The name muonium can cause a little confusion, because several similarly named objects exist. A muonic atom is usually an ordinary atom in which a negative muon replaces an electron. In that situation, the nucleus still contains protons and neutrons, while the negative muon moves very close to it. Muonium is different. It contains no proton and no neutron. Its two ingredients are only the positive muon and the electron. There is also something sometimes called true muonium, which is a bound system made from a negative muon and a positive muon. Despite the dramatic name, ordinary muonium is the established name for the positive muon and electron combination. Scientific naming grew through history, rather than through a committee determined to make bedtime explanations easy, so a little untangling is sometimes necessary. The simplicity of muonium is one of the main reasons physicists care about it. A proton may look like a single point in a simple drawing, but it has an internal structure. It is built from quarks and gluons, and its size and internal behavior affect extremely precise measurements of hydrogen. Those effects are fascinating, but they also add complexity when scientists want to test the laws governing charged particles. The electron and the muon are different. As far as current experiments can determine, both behave as elementary particles. They do not appear to contain smaller components. Muonium therefore gives researchers a hydrogen-like atom without the complicated internal structure of a proton. It is a clean system in which the interaction between two leptons can be calculated and measured with exceptional care. This does not make muonium easy to study. Clean in theory does not mean convenient in a laboratory. The positive muon decays naturally after an average time of about 2.2 millionths of a second. When it decays, the muonium atom no longer has its heavy positive center, so the bound system ends. Scientists must create the muons, slow them down, help them capture electrons, and perform their measurements before the internal clock of the muon runs out. That is rather like being asked to build a watch, read the watch, and write down the result before someone finishes blinking, except that the laboratory repeats the process again and again. One muonium atom provides only a tiny amount of information. A large stream of atoms, produced under controlled conditions, can reveal a clear pattern. The short lifetime also makes muonium a useful meeting point between atomic physics and particle physics. Atomic physics asks how the electron and positive muon bind together, which energy states are available, and how the atom responds to light and magnetic fields. Particle physics asks what the muon is, how it decays, whether it follows the expected symmetries, and whether unknown interactions slightly alter its behavior. Muonium lets these questions occupy the same experimental object. Imagine that you wanted to test the accuracy of a musical instrument. You could play a note, compare it with a trusted reference, and listen for a slight difference in pitch. Muonium spectroscopy follows a related idea, although the listening is done with equipment rather than ears. The atom can change from one allowed energy state to another when it interacts with radiation of the right frequency. By finding that frequency with great precision, researchers can compare the measured result with the prediction from quantum electrodynamics, the theory describing interactions between charged particles and light. any disagreement would be important. It might mean that some part of the calculation needs improvement. It might show that an experimental effect has been overlooked. In the most exciting case, it could suggest an interaction that is missing from the current description of particle physics. Scientists do not begin by assuming that every small mismatch is a doorway to a new universe. Most mismatches turn out to have much more ordinary explanations. A detector may need recalibration, a gas pressure may shift the result, a magnetic field may be slightly uneven. Physics advances through enthusiasm, but it survives through suspicion. Muonium is also valuable because the muon is similar to the electron while being much heavier. Both particles have the same amount of electric charge, apart from the sign when we compare their matter forms. Both belong to the lepton family. Both appear elementary. Yet the muon has far more mass and is unstable, while the electron is the durable particle that fills atoms, carries electric current and makes ordinary chemistry possible. Why nature contains these heavier relatives is still a deep question. The electron is enough to build atoms and molecules. The muon seems at first like an unnecessary copy that arrives, lives briefly, and disappears. It is the particle equivalent of buying a second kettle that is much heavier, works only for a moment and cannot remain in the kitchen. Yet that heavier copy gives physicists a new way to test whether the rules applied to electrons also apply to muons. Muonium makes that comparison especially precise. The electron and positive muon are held together mainly by electromagnetism. Their spins, which are intrinsic quantum properties, interact with each other. Their masses influence the atom's energy levels. Their magnetic behavior affects how the system responds to external fields. Each measurement becomes a way of asking whether the muon follows the same framework as the electron, adjusted for its greater mass and opposite charge. The phrase atom made of matter and antimatter may also lead to a second misunderstanding. Muonium is not half ordinary substance and half a stored supply of destructive energy in the everyday sense. At this scale, matter and antimatter are labels for particles and their corresponding partners. The electron is matter. The positive muon is antimatter. Together they form a neutral atom because their electric charges cancel. The object is unusual, but it is not constantly struggling against itself. Nor does Muonium explain why the visible universe contains much more matter than antimatter. That larger mystery concerns the early universe and the processes that may have treated matter and antimatter slightly differently. Muonium contributes to the broader investigation by allowing precise tests of symmetries and particle properties. It is one instrument in a much larger orchestra, and it does not claim the entire solo. There is something appealingly direct about using such a tiny object to investigate such large questions. Researchers do not need Muonium to last for years. They need it to behave predictably for a very short time. During that interval, the atom carries information about electric charge, mass, magnetism, quantum states, particle decay, and the relationship between matter and antimatter. A few millionths of a second may feel almost meaningless in daily life. It is shorter than any conscious reaction you can make. You cannot press a button that quickly after seeing a light. You cannot notice a sound, decide what it was, and finish a thought before the atom is gone. But the machinery of a particle experiment does not wait for human awareness. Detectors register signals, timing systems sort events, and computers combine results from enormous numbers of repeated encounters. The atom's brief existence is therefore not a failure of stability, it is simply the consequence of using a muon. The electron is not the problem. Left on its own, an electron is stable as far as we know. The positive muon is the temporary guest. It eventually decays into other particles, and when that happens, the atomic arrangement cannot continue. This gives Muonium an odd balance of familiarity and strangeness. Its shape and energy structure resemble hydrogen. Its ingredients belong to particle physics. Its center is antimatter. Its outer particle is matter. It survives because the two are not direct opposites of the same species. It disappears because the muon decays. not because the atom suddenly loses an argument with annihilation. Knowing this changes the central question. We no longer need to ask how matter and antimatter can touch without immediately destroying everything. We can ask something more precise. How does a positive muon, born in a high-energy process and destined to survive for only a tiny fraction of a second, slow down enough to capture an electron? How do two particles that were not created as an atom find each other and settle into a bound quantum state? How can researchers prepare enough of these temporary atoms to measure them before they vanish? To answer that, we need to meet the muon before it becomes the centre of muonium. We need to see where positive muons come from, how they move through matter, why they lose energy, and what must happen during the brief interval when one of them encounters an electron and becomes for a moment something very much like hydrogen. The meeting that creates muonium does not begin with an electron waiting patiently beside an empty chair. It begins much farther away, inside a large accelerator facility, where ordinary protons are pushed to high energy and directed into a solid target, often made from carbon. The collision produces a crowded spray of short-lived particles. Among them are pions, and the positive pions are especially useful because they can decay into positive muons. This is an important detail. The accelerator does not usually manufacture muons in a single direct step. It first produces pions, and then nature completes the next part. A positive pion survives for only a tiny fraction of a second before changing into a positive muon and a neutrino. The neutrino leaves almost without interacting with anything. The positive muon, being electrically charged, can be guided, focused, slowed, and delivered to an experiment. Some of the most useful positive muons come from pions that stop close to the surface of the production target before they decay. Because the pion is nearly at rest, the muon leaves with a fairly well-defined amount of motion. These are called surface muons. The name sounds pleasantly gentle, as though they have been found resting beside a pond, but they are still moving at an impressive speed when they enter the beamline. The beamline is a carefully arranged path made from magnets, vacuum pipes, detectors, and other equipment. Charged particles do not all travel in the same direction after the collisions, so magnetic fields are used to select and steer the ones the researchers want. Unwanted particles are filtered away as much as possible. The positive muons are focused into a beam and sent toward a chosen material. There is another useful feature already built into many positive muon beams. The muons can be strongly spin polarized. Spin is an intrinsic quantum property, not a literal ball turning around an axis, although the word has encouraged generations of drawings that suggest exactly that. A polarized beam means that the spins of many muons begin with a shared orientation. This gives the experiment a known starting condition, which later helps scientists follow what happens inside the material. By the time the muon reaches the target used to create muonium, the clock is already running. A positive muon has an average lifetime of about 2.2 millionths of a second. That is long by the standards of many unstable particles, but it leaves no room for administrative delays. The muon cannot be asked to wait while someone adjusts a cable or looks for the correct laboratory notebook. Everything must already be prepared. The incoming muon enters the material as a fast, positively charged particle. It does not immediately capture the first electron it passes. At high speed, it travels through the electronic surroundings of the material and loses energy through repeated interactions. It can disturb atoms, excite electrons, and knock some electrons free. Each interaction removes a little of the muon's motion until it becomes much slower. You can picture the muon entering a crowded room at running speed. At first, it cannot settle into a conversation with anyone. It bumps past chairs, sends papers flying, and causes several people to wonder who approved the guest list. Only after it slows down can it remain near one electron long enough for a bound state to form. The comparison is not exact, but it has the advantage of requiring no advanced mathematics and only minor damage to office furniture. As the muon loses energy, it leaves behind what researchers call an ionization track. This is a trail of disturbed atoms, positive ions, and displaced electrons created along its path. The track matters because one of those electrons may later become the electron in muonium. The atom can therefore be assembled from the incoming muon and an electron that the muon itself helped remove from the surrounding material. The slowing process is extremely fast. Long before the muon reaches the end of its natural lifetime, it can lose most of its initial motion and approach the energy scale of the material around it. Physicists often describe this as thermalization. It does not mean the muon has become warm and comfortable in any human sense. It means that its random motion is no longer enormously greater than the motion associated with its environment. Muonium can form at different stages of this slowing process. In some cases, the positive muon captures an electron while it is still moving with more energy than the surrounding particles. This is often described as prompt formation. In other cases, the muon slows first and later encounters an electron from its ionization track. This delayed route depends strongly on how easily electrons can move through this material and whether they become trapped before reaching the muon. That makes the birth of muonium partly a question about the environment. The positive muon and electron have opposite electric charges, so attraction encourages them to come together, but the surrounding material can help, hinder, or completely reshape that meeting. Electrons may be mobile or tightly bound. They may become trapped at defects. Other atoms may capture them first. Electric fields can pull them away from the muon or push them toward it. Temperature can change how quickly they move. In a suitable insulating material, a positive muon may readily acquire an electron and form neutral muonium. In a metal, the situation is different because the large population of mobile electrons screens electric charges and interacts strongly with the implanted muon. A neat, isolated muonium atom is usually not observed there in the same way. Instead, the muon behaves as a charged probe within the sea of conduction electrons. Nature has provided the ingredients, but the kitchen is too crowded for the usual recipe. Gases can also produce muonium. A positive muon moving through a gas loses energy through collisions and can capture an electron from a gas atom or molecule. Some gases allow muonium to form very efficiently. Early experiments used this behavior to identify muonium through changes in the muon spin motion. The newly formed atom responded to magnetic fields differently from a bare positive muon, revealing that an electron had joined it. The phrase "capture an electron" may sound as though the muon reaches out with a tiny hand. What really happens is a quantum transition from an unbound arrangement to a bound one. Before the transition, the electron and muon are separate particles moving through their environment. Afterward, their shared state has the structure of an atom. Energy and momentum must still be conserved, so the excess energy is transferred to the surroundings, to another particle, or through radiation, depending on the method and environment. The electron does not spiral inward like a marble circling a drain. That familiar picture belongs to classical motion and fails at atomic scales. The electron changes into a bound quantum state associated with the positive muon. Its possible locations are spread around the muon, and the pair acquires a set of allowed energy levels. Muonium is born when the system enters one of those bound arrangements. Sometimes the first arrangement is not the lowest energy state. Production methods can create excited muonium, with the electron in a higher energy state. The atom may then release energy and move to a lower state. Many precision experiments are designed to study particular transitions, so researchers care not only about whether muonium forms, but also about which state it occupies and how cleanly that state can be prepared. Creating muonium inside a solid is useful for studying the solid itself. Once formed, the atom can sit at a particular location in a crystal, move between sites, react with defects, or exchange charge with its surroundings. Because muonium behaves chemically like a very light relative of hydrogen, it can reveal how hydrogen might behave in semiconductors, insulators, and other materials. The muon then decays, and the emitted positron carries information about the muon spin at the moment of decay. The detection method takes advantage of the fact that positive muon decay is not directionally indifferent. The positron is more likely to emerge in a direction related to the muon spin. Detectors placed around the sample record many decay positrons. From their changing pattern over time, researchers reconstruct how the muon spin evolved. If muonium formed, the interaction between the electron spin and the muon spin changes that evolution in a recognizable way. This is one reason the initial polarization of the beam is so valuable. The experiment begins with many muon spins pointing in a known direction. After implantation, magnetic fields inside the sample and the presence or absence of a bound electron alter their motion. The positron detectors do not take a photograph of a tiny atom. They watch a statistical signal built from a large number of decays. Muonium announces itself through a pattern. For precision spectroscopy, however, scientists often want muonium outside the complicated environment of a solid. Collisions with nearby atoms can shift its energy levels or disturb its spin. A material that helps create muonium may also interfere with the measurement immediately afterward. The challenge is therefore to produce the atom in a material and then persuade it to leave. Silica aerogel has become especially useful for this purpose. Aerogel is a solid network filled with a vast number of tiny pores. It is so light that a block can look as though someone attempted to make glass from fog and stopped just before the fog became practical. A positive muon enters the aerogel, slows down and may capture an electron. The resulting neutral muonium atom can move through the pore structure. Because muonium is electrically neutral overall, electric fields do not steer it as easily as they steer a bare positive muon. It moves through the aerogel mainly through collisions and diffusion. If it reaches an internal surface connected to open space, it may escape into the surrounding vacuum. Once there, the atom is much less affected by neighbouring matter, giving lasers and microwave fields a cleaner target. The escape is not guaranteed. Aerogel contains a large internal volume, and an atom born too deep inside may decay before finding a route out. Remember that the positive muon continues to carry its 2.2 millionth of a second average lifetime even after muonium forms. The atom is not granted extra time for good behaviour. Researchers therefore design the material to improve the chance that muonium forms close enough to a surface and reaches vacuum quickly. One approach is to create small holes or channels in the aerogel surface. These openings increase the accessible surface area and shorten the distance a muonium atom may need to travel before escaping. Laser processing can make a pattern of tiny holes without turning the delicate aerogel into an expensive pile of dust. Experiments have shown that such structures can improve the emission of muonium into vacuum. Temperature also affects what happens next. Muonium leaving a porous material can carry an energy distribution related to the temperature of the source. For some experiments, researchers want slow muonium because slower atoms spend more time in the region where lasers or microwave fields can interact with them. A fast atom crosses the measurement zone quickly, rather like a guest who arrives, checks the clock and leaves before the tea is poured. Other production techniques use thin foils or gas targets. A low-energy positive muon can pass through a thin material and emerge after capturing an electron. Beam foil methods can produce muonium in excited states. Gas-based charge exchange can create a beam of neutral muonium. Each technique offers a different balance between formation efficiency, atomic speed, state preparation, and background signals. There is no single best birthplace for every muonium experiment. A study of how hydrogen behaves in a semiconductor may want the muonium to remain inside the material. A measurement of atomic energy levels may want it in vacuum. An experiment that uses muonium as a step toward producing extremely slow positive muons may create the atom, let it emerge from aerogel, and then remove the electron again with carefully tuned laser light. That last procedure may seem unnecessarily complicated. The facility begins with a positive muon, adds an electron to make muonium, and then removes the electron to recover a positive muon. It resembles preparing a sandwich only to take the filling out again. The purpose is not the final charge alone. Forming neutral muonium allows the system to cool and escape from a material in a useful way. Removing the electron afterward produces a much slower and more controlled positive muon beam than the original one. The laser must arrive at the right moment and with the right frequencies. One part of the light lifts the electron into an excited state, and another removes it from the atom. The positive muon left behind can then be accelerated by electric fields. Recent accelerator work has used this approach to create slow muons suitable for further acceleration, showing how the temporary atom can serve as a bridge between a conventional muon beam and a more precisely controlled one. Even without that extra step, the timing of a Muonium experiment is a carefully managed sequence. A detector records the arrival of a muon. The muon enters the target and slows. Muonium forms. It may diffuse into vacuum. A pulse of laser light or a microwave field interacts with it. The muon eventually decays. Positron detectors record the decay, and the system decides whether the event belongs to the signal being studied. No individual atom explains very much. The useful result appears only after the sequence has been repeated many times. Researchers compare events with different laser frequencies, magnetic fields, gas pressures, temperatures, or target designs. A small change in the positron pattern may reveal that a transition occurred. A change in the formation fraction may show how electrons move in a material. A difference in vacuum emission may show that a new pore structure works better. The muon's ionization track can be especially informative. Since the muon creates free electrons while slowing down, the eventual formation of muonium can reveal whether those electrons remain mobile. If an external electric field pulls the electrons away, delayed muonium formation may decrease. If the field pushes them toward the stopped muon, the formation probability may rise. The atom's birth then becomes a microscopic test of electron transport. Impurities and defects matter as well. A missing atom in a crystal, a foreign atom in the lattice, or a region with trapped charge can alter where the muon stops and whether an electron reaches it. Muonium may form in more than one local arrangement, each with a different interaction between the electron and the surrounding material. Scientists can use those differences to identify otherwise hidden features of the sample. This also explains why the simple statement that a muon meets an electron leaves out most of the interesting work. The two particles do not begin as a prepared pair. The muon is produced through pion decay, selected by a beamline implanted into matter, slowed through countless interactions and surrounded by a track of disturbed charge. The electron may come from that track, from a nearby atom, or from a controlled charge exchange process. The material determines whether the meeting becomes a bound state for the short lifetime available. Stable here is a relative word. Once formed, muonium can remain bound until it is disturbed, reacts, loses its electron, or reaches the inevitable decay of the muon. Compared with the slowing and capture processes, a few millionths of a second is enough for a surprising amount to happen. The atom can cross a small vacuum region, absorb light, change its spin state, collide with surfaces, or participate in chemical reactions. Nothing about its formation requires matter and antimatter to ignore the usual laws. The positive muon and electron attract because their charges are opposite. They avoid direct annihilation because they are not each other's matching particle and antiparticle. Quantum mechanics supplies the allowed bound states. The surrounding environment carries away energy and shapes the probability that capture occurs. Particle decay sets the final time limit. After all of that preparation, the result can look almost ordinary. There is a positive center and a negative electron. The atom is neutral. Its energy levels resemble those of hydrogen. Light can move it between allowed states. Magnetic fields can alter the way its spins behave. Yet the positive center is not a proton. It is an elementary antimatter particle with only a fraction of the proton's mass and a lifetime measured in millionths of a second. That difference changes almost every precise detail. It changes how strongly the two particles move around their common center. It changes the spacing of the atomic energy levels. It changes the magnetic interactions. It removes the internal structure that complicates measurements involving a proton. It turns a familiar atomic arrangement into one of the cleanest laboratories available for testing the behavior of leptons. So when a muon meets an electron, the meeting is not merely a collision. Under the right conditions, it becomes an atom. The muon brings its charge, mass, spin, and limited lifetime. The electron brings the familiar quantum behavior that shapes ordinary chemistry. The laboratory brings the beam, the target, the timing, and the detectors. Together they create an object that resembles hydrogen closely enough to feel familiar, while differing from it in ways that make every measurement more revealing. To understand why physicists call muonium a strange cousin of hydrogen, we now need to look more closely at the two particles after the meeting has taken place. Their charges may copy the basic pattern of hydrogen, but their masses, motions, magnetic properties, and lack of internal structure give the atom a character entirely its own. To see why physicists call muonium a strange cousin of hydrogen, it helps to place the two atoms beside each other and remove every detail that's not essential. Ordinary hydrogen contains one proton and one electron. Muonium contains one positive muon and one electron. Both systems have a heavy positive particle near the centre and a much lighter negative particle bound to it. Both are electrically neutral. Both have a single electron, so many of their atomic patterns look closely related. That simple comparison is accurate, but it can also hide the most interesting difference. The central particle in hydrogen is a proton. The central particle in muonium is a positive muon, which is the antimatter partner of the negative muon. A proton is a composite particle made from quarks and gluons. A positive muon, as far as present experiments can determine, has no smaller internal components. It behaves as an elementary particle. This means muonium does not contain a conventional atomic nucleus. There is no cluster of protons and neutrons at its centre. There is only the positive muon, acting as the positive centre around which the electron is bound. Physicists still call muonium an atom because it has an atomic bound state, complete with energy levels, spin interactions, and transitions that can be studied with light and magnetic fields. It simply replaces the usual nuclear centre with a single elementary particle. The electric charges match the basic pattern of hydrogen. The electron carries 1 unit of negative charge. The positive muon carries 1 unit of positive charge. The two charges cancel when the atom is viewed from a distance, leaving muonium neutral overall. This is why a finished muonium atom does not respond to electric fields in the same simple way as a bare positive muon. Its internal charges can still be affected, but the object as a whole has no net charge. The positive muon has the same mass as the negative muon, just as an antiparticle is expected to have the same mass as its matter partner. It is much heavier than an electron but much lighter than a proton. A muon has a mass a little more than 200 times the mass of an electron. A proton has a mass more than 1800 times the mass of an electron. Put another way, the positive muon is only about 1/9 as massive as the proton. That mass difference makes muonium far lighter than ordinary hydrogen. Most of the mass of hydrogen sits in the proton. Most of the mass of muonium sits in the positive muon, but that muon is still much lighter than a proton. The complete muonium atom therefore has only a little more than 1/9 of the mass of a hydrogen atom. Calling muonium a light version of hydrogen is useful, although it should not be taken to mean that someone has shaved material from a proton. The positive muon is not a smaller proton, it belongs to a different particle family. The proton is a hadron, meaning that it participates in the strong interaction through its quark structure. The muon is a lepton. It belongs to the same broad family as the electron, and does not participate in the strong interaction in the same way. The electron and the muon are sometimes described as relatives from different generations. The electron belongs to the first generation of matter particles. The muon belongs to the second. They have the same electric charge when both are considered in their negative matter forms, and they share several basic quantum properties. The muon is heavier and unstable, while the electron is light and stable. Nature appears to have repeated part of its particle design at a larger mass, rather like printing a second edition that is heavier, shorter lived, and much harder to keep on a shelf. In muonium, of course, the particle at the centre is the positive antimatter form of that heavier relative. The electron remains an ordinary matter particle. Their opposite charges produce attraction, but their different identities prevent direct electron and positron annihilation. The positive muon is not a positron. It is the antiparticle of a negative muon, so the atom contains matter and antimatter without containing a particle beside its own matching antiparticle. Once bound, the electron does not follow a small circular track around the muon. Atomic diagrams often draw neat rings because they are easy to recognize, not because electrons actually move like planets. Quantum mechanics describes the electron through a wave function, which gives the probabilities for finding it in different regions around the positive muon. In the lowest energy state, that probability is spread smoothly around the center. The positive muon is not perfectly motionless either. In hydrogen, the proton is so much heavier than the electron that introductory explanations often treat it as fixed. That approximation works well for many purposes, although the proton does move slightly. In muonium, the central particle is much lighter, so its motion matters more. The electron and positive muon both move around their shared center of mass. Imagine two people on a smooth floor holding opposite ends of a rope. If one person is much heavier, the lighter person travels through most of the motion while the heavier person shifts only a little. If their masses become less unequal, both move more noticeably. The electron and muon are still very unequal in mass, but not as extremely unequal as the electron and proton. Muonium therefore behaves more like a genuine two-body dance than the simplest picture of hydrogen suggests. This shared motion affects the size and binding of the atom. Muonium is slightly larger than ordinary hydrogen in its lowest state, and its electron is slightly less tightly bound. The difference is small, only a fraction of 1%, but precision spectroscopy can detect it. What looks almost identical in a simple sketch becomes measurably different when researchers examine the exact frequencies of atomic transitions. The allowed energy states follow the same general organization found in hydrogen. The electron can occupy a lower state or higher excited states. It can absorb the correct amount of energy and move upward. It can later release energy and return to a lower state. Because the central mass differs, the spacing between those states is not exactly the same as in hydrogen. These small shifts are not unwanted imperfections. They are part of the reason muonium is useful. The transition frequencies depend on the masses of the electron and muon, so measuring them can provide a precise value for the muon mass. The calculations also depend on quantum electrodynamics, the theory of electrically charged particles interacting through light. Agreement between prediction and measurement tests how well that theory describes a bound system made entirely from leptons. The word entirely matters here. Hydrogen contains an electron, which is elementary, and a proton, which has internal structure. That internal structure slightly affects hydrogen energy levels. The proton has a finite size. Its electric charge and magnetism are distributed through a complicated object made from quarks and gluons. At ordinary scales, the proton still behaves like a compact positive particle. At very high precision, its internal details can no longer be ignored. Muonium avoids much of that complication. Both of its ingredients are leptons and appear point-like at the scales reached by experiments. There is no proton radius to include, and no nuclear structure made from quarks to model. The atom is not perfectly simple, because quantum effects can become very detailed, but its ingredients are cleaner. That gives theorists an unusually direct system to calculate. It also gives experimentalists fewer places for disagreement to hide. If a measured muonium transition differs from the best prediction, researchers cannot immediately blame an uncertain proton size. They must inspect the experiment, the calculation, and the possibility of effects beyond the expected interactions. Most investigations still end with ordinary explanations, but the absence of nuclear structure makes the comparison unusually sharp. Mass is not the only important property. The electron and positive muon each possess spin. Spin is an intrinsic form of quantum angular momentum. It does not mean that either particle is a tiny solid sphere rotating at the surface. The name survives because the mathematical behavior resembles some features of rotation, while the physical object refuses to cooperate with the familiar picture. Each spin gives the particle a magnetic moment, so the electron and muon behave in some ways like tiny magnets. In muonium, those magnetic moments interact. The spins can be arranged in different relative orientations. One broad arrangement has them aligned in the same general direction. Another has them opposed. These arrangements have slightly different energies. That difference creates what is called hyperfine structure. The word hyperfine may sound as though ordinary fine structure was not considered sufficiently fine, and historically, that is not far from how the naming developed. It refers to a very small splitting of atomic energy levels caused by magnetic interactions involving the particle spins. Muonium hyperfine structure is one of its most important measurable features. Researchers place muonium in a controlled magnetic field and expose it to microwave radiation. When the microwave frequency matches the energy difference between particular spin states, transitions occur. By observing those transitions, scientists can determine properties such as the muon magnetic moment and test detailed predictions of quantum electrodynamics. The positive muon eventually decays, but its decay helps reveal the spin information. The emitted positron tends to leave in a direction connected to the muon spin. Detectors surrounding the experiment record the changing pattern of those positrons. The atom is gone by the time the signal reaches the electronics, yet the direction of the decay products preserves evidence of what the muon was doing immediately before it disappeared. Muonium is often treated as an extremely light isotope of hydrogen when it enters a material or takes part in chemical reactions. Strictly speaking, it is not a normal hydrogen isotope. Isotopes are forms of the same element whose nuclei contain the same number of protons but different numbers of neutrons. Muonium has no proton at all, so it does not satisfy that nuclear definition. Chemically, however, the comparison works surprisingly well. Chemical behaviour is governed mainly by electrons, especially the outer electrons that form bonds. Muonium has one electron and one positive centre, giving it the same basic electronic arrangement as hydrogen. It can replace hydrogen in certain molecules and occupy sites that hydrogen might occupy in a solid. For that reason, chemists and material scientists often use muonium as a light hydrogen analogue. It can form muonium-containing molecules, react with organic compounds, and become trapped at particular locations in crystals. Studying its spin signal can reveal how hydrogen-like species move and react in environments that are difficult to examine by other methods. Its unusually low mass produces a very large isotope effect. In ordinary chemistry, replacing hydrogen with deuterium changes the nuclear mass by roughly a factor of 2. Replacing hydrogen with muonium changes the effective central mass by roughly a factor of 9. Vibrations, tunneling behaviour, reaction rates, and motion through materials can therefore differ strongly. A molecule containing muonium does not merely behave like the same hydrogen molecule with a label changed in the laboratory record. The lighter positive centre moves more readily. Bonds involving it can vibrate at different rates. Quantum tunneling, in which a particle passes through a barrier that classical physics would forbid it from crossing, can become more prominent. These effects allow researchers to test how mass influences chemical reactions. The situation can feel slightly backwards. A muon is much heavier than an electron, so particle physicists often describe it as a heavy electron relative. Inside chemistry, the same muon is much lighter than a proton, so muonium behaves as an exceptionally light hydrogen relative. The particle has managed to be both heavy and light, depending on which family photograph is being discussed. Several other exotic atoms are easy to confuse with muonium, and separating them helps clarify what the atom is made of. Positronium contains an electron and a positron. Those two particles are direct matter and antimatter partners, so they eventually annihilate. Because their masses are equal, both move equally around their shared centre. Muonium contains an electron and a positive muon. Their masses are not equal, and they are not direct partners. The positive muon usually disappears through its own decay, rather than through annihilation with the electron. The atom therefore has a different lifetime, different energy structure, and different scientific uses from positronium. Monic hydrogen is another separate system. It contains a proton and a negative muon. The negative muon takes the role normally occupied by an electron, but because it is much heavier, it remains far closer to the proton. That closeness makes monic hydrogen very sensitive to the proton size. Muonium reverses the placement. Its muon is positive and sits at the centre, while an ordinary electron forms the outer part of the atom. Antimonium is the charge reverse counterpart of muonium. It would contain a negative muon and a positron. Muonium and antimonium have corresponding structures, with matter and antimatter roles exchanged. Searches for muonium changing spontaneously into antimonium are important because such a process would violate expected rules involving lepton family numbers. For the moment, it is enough to keep the ingredients straight. Muonium means a positive muon with an electron. The atom is sometimes given a chemical-style abbreviation made from the first two letters of its name. That shorthand is convenient in laboratory papers, especially when muonium is placed inside a molecule. It should not be mistaken for a new entry on the periodic table. Muonium has no atomic number because it has no proton. It is an exotic atomic system, not an element that can be mined, stored, or added to breakfast cereal. Its lack of a proton also means that the usual boundary between atomic and particle physics becomes less clear. The electron belongs comfortably to atomic physics because electrons shape atoms and chemistry. The positive muon arrives from a particle accelerator and carries the instability of a fundamental particle. Bind them together, and the result asks questions from both subjects at once. Atomic theory describes the bound states. Particle theory describes the muon and its decay. Electromagnetism holds the system together. The weak interaction eventually destroys the central particle. Quantum mechanics determines the allowed arrangements. Relativity and quantum field effects provide smaller corrections that precision experiments must include. This combination is why muonium can be simple without being boring. It has only two constituents, yet each measurable detail can test a different part of physics. Its transition frequencies depend on particle masses. Its hyperfine splitting depends strongly on magnetic moments and spin interactions. Its response in materials reveals local magnetic fields and electron behavior. Its possible conversion into antimunium tests, where the particle identities are conserved as expected. Even the question of its size leads back to the motion of both particles. Since the positive muon is lighter than a proton, it is pulled around more strongly by the electron. The atom cannot be described as an electron moving around a completely fixed point. The centre itself participates, and the measured spectrum carries the evidence. At a casual glance, hydrogen and muonium seem almost interchangeable. Each contains one positive object and one electron. Each is neutral. Each supports a familiar ladder of atomic states. If atoms had silhouettes, the two would be difficult to distinguish from across the room. Closer inspection changes the picture. Hydrogen has a composite nuclear centre that is stable and heavy. Muonium has an elementary antimatter centre that is lighter and temporary. Hydrogen can survive indefinitely under suitable conditions. Muonium inherits the muon's short lifetime. Hydrogen anchors ordinary chemistry across the universe. Muonium appears briefly in controlled experiments and unusual material environments. The resemblance is therefore real, not superficial, but it is a resemblance built around electric charge rather than shared nuclear identity. The electron sees a positive charge and forms a hydrogen-like bound state. It does not require the positive centre to be a proton. Electromagnetism provides the family resemblance, while mass, spin, internal structure, and stability provide the differences. Those differences become especially important once the atom has formed and the experiment begins counting time. The electron may be stably bound, the energy levels may be well defined, and the atom may behave predictably, but the positive muon still carries the decay clock it had before capture. Becoming part of an atom does not pause that clock. It does not make the muon stable or persuade the weak interaction to take the evening off. Every measurement must therefore fit inside a lifetime that averages only a little more than 2 millionths of a second. That interval is short for human experience, but long enough for atomic motion, spin changes, collisions, chemical reactions, and carefully timed spectroscopy. The next question is not simply why muonium dies so soon, it is how so much useful physics can happen before it does. That useful interval begins the instant muonium forms. The electron has joined the positive muon, the bound atomic state has appeared, and the experiment finally has the object it was designed to study. At the same moment, nothing has changed about the most inconvenient property of the positive muon. It is still unstable. Becoming the centre of an atom does not make it permanent, and the electron cannot protect it from decay. The average lifetime of a positive muon at rest is about 2.2 millionths of a second. Muonium inherits almost exactly the same lifetime, because the positive muon is the temporary part of the atom. The electron may remain stable, the atomic binding may be well defined, and the surrounding laboratory may be controlled with extraordinary care, but the weak interaction continues working inside the muon, according to the same rules it followed before the atom formed. 2.2 millionths of a second is difficult to imagine directly. Human reactions are much slower. A blink may last a tenth of a second or longer, which is tens of thousands of muonium lifetimes. The shortest pause in an ordinary conversation is an enormous stretch of time by comparison. Even the click of a camera shutter can be leisurely beside the life of this atom. It would be reasonable to assume that nothing complicated could happen in such a short interval. At atomic scales, however, a millionth of a second is not a tiny allowance. Changes inside atoms often occur in far smaller fractions of a second. Light can interact with the electron. The spins of the electron and muon can change their relative behaviour. The atom can move through a gas, cross a small region of vacuum, collide with another particle, or respond to a magnetic field. A great deal of microscopic activity can fit inside a period that human senses cannot separate from an instant. The lifetime is an average, not an appointment. A newly formed muonium atom does not receive a message saying that its muon will decay exactly 2.2 millionths of a second later. Quantum decay is random for each individual particle. One muon may disappear almost immediately. Another may survive several times longer than the average. There is no visible sign that tells the experiment which one is about to go. Across a large population, the randomness produces a reliable pattern. Many atoms disappear early, fewer remain as time passes, and the surviving population decreases in a smooth and predictable way. After one average lifetime, a little more than 1/3 of the original muons are still present. After another equal interval, only a much smaller fraction remains. The experiment cannot extend the life of an individual atom by planning carefully, but it can predict how many atoms should still be available at each stage of the measurement. This distinction between an individual event and a large collection is central to particle physics. The decay time of one muon is unpredictable. The distribution of decay times for millions of muons can be measured with impressive precision. It is rather like watching raindrops strike a roof. You cannot say exactly when one particular drop will land, but the total pattern can become steady enough to measure. What actually happens when the positive muon decays is very different from annihilation. The electron in muonium does not meet its own antiparticle, and the two constituents do not convert all their mass into light. Instead, the positive muon changes through the weak interaction. It produces a positron, an electron neutrino, and a muon antineutrino. The positron is the antimatter partner of the electron. It carries positive electric charge and can be detected because it interacts readily with matter. The two neutrinos carry no electric charge and interact so weakly that they usually pass through the apparatus without leaving a measurable trace. They carry away energy, momentum, and information required by the conservation rules of particle physics, but the detector normally sees only the positron. The original electron from muonium is left without its positive centre. Once the muon has decayed, the atomic binding no longer exists. The electron becomes free or interacts with the surrounding material. The muonium atom has ended, not because its two original particles annihilated each other, but because one constituent changed into a different set of particles. That final moment is also the experiment's most useful signal. Positive muon decay has a directional preference connected to the muon spin. The positron is more likely to emerge in one direction relative to the spin than in the opposite direction. This preference comes from the way the weak interaction treats spatial directions and particle handedness. For the laboratory, the important result is simple. The direction of the outgoing positron carries information about the direction of the muon spin just before decay. Detectors placed around the sample record where and when the positrons arrive. One decay tells researchers very little because the positron direction is still probabilistic. Millions of decays build a pattern. If the muon spins are turning in a magnetic field, the preferred direction of positron emission turns with them. The detector counts rise and fall in a way that reveals the spin motion. Muonium therefore reports on its own brief life at the moment that life ends. The positive muon acts as part of the atom, responds to the electron and the surrounding fields, and then produces a positron that carries the final spin information out to the detectors. It is a remarkably cooperative arrangement for a particle that cannot be persuaded to remain for more than a few millionths of a second. The electron and muon spins interact throughout the atom's lifetime. In a magnetic field, their combined state can change in time. Depending on the field strength and the atomic state, the spin signal may oscillate at characteristic frequencies. Researchers measure these oscillations by sorting positron detections according to the time elapsed after each muon entered the target. The clock for an event often starts when an incoming muon passes through a thin detector or reaches the experimental sample. Electronics record that arrival. When a positron is detected later, the system records the delay. Repeating this process creates a time histogram, a count of how many positrons appeared after different waiting intervals. At early times, many muons remain, so many decays are recorded. At later times, fewer survive. The overall number falls, but the directional pattern may also contain oscillations or gradual changes caused by spin rotation and relaxation. The experiment must separate those features from the simple loss of muons through decay. Relaxation in this setting does not mean that the atom has become comfortable. It means that an initially organized group of spins gradually loses its shared alignment. Slight differences in local magnetic fields can make individual spins turn at different rates. Collisions can disturb the electron. Chemical reactions can change the state of the muonium. The detector then sees the collective signal fade more quickly, even though the muons themselves still follow their ordinary decay lifetime. This produces an important difference between the lifetime of the muon and the lifetime of a particular muonium state. The positive muon may survive while the atom is ionized and loses its electron. Muonium may react with a molecule and become part of a new chemical species. It may strike a wall, become trapped, or move into an environment where its original spin pattern is no longer recognizable. In those cases, the muonium state being studied has ended, even though the muon has not yet decayed. Experimentalists must account for all of these competing processes. If the muonium signal disappears quickly, that does not automatically mean that the muon lifetime has changed. It may mean that the atoms left the observation region, reacted with the gas, collided with a surface, or lost their spin polarization. The detector is measuring a combination of particle decay, atomic motion, and environmental effects. Vacuum experiments reduce many of those complications. Muonium emitted from a porous material into vacuum has fewer collisions than muonium inside a solid or gas. Lasers can interact with it without large shifts caused by neighboring atoms. Even there, geometry matters. An atom may move out of the laser region before the muon decays. It may hit a chamber wall. The available observation time is set both by the muon lifetime and by how long the atom remains in the right place. This is why slow muonium is valuable. A slower atom spends more time crossing the region, illuminated by a laser or exposed to a microwave field. More interaction time can produce a stronger signal and a narrower measurement of a transition. The atom is still short-lived, but the experiment uses a larger fraction of that brief life. The timing of laser pulses must be matched to the muon beam. At a facility that delivers muons in pulses, many muons arrive within a defined interval. Researchers can trigger laser light after a chosen delay, allowing time for the muons to stop, capture electrons, and for some muonium atoms to escape into vacuum. Fire the laser too early, and the atoms may not be ready. Fire it too late, and too many muons will already have decayed. There is no single perfect delay because formation and emission also take time. Some atoms appear promptly, others form after electrons return along the ionization track. Some escape the material quickly, others wander through pores before reaching the surface. The experiment chooses a timing window that captures the best balance between the number of atoms and the cleanliness of the signal. The short lifetime also influences the size of the apparatus. A thermal muonium atom can travel only a limited distance before its muon is likely to decay. The useful region is therefore often measured in millimeters or centimeters rather than meters. Researchers place targets, laser paths, microwave cavities, and detectors close together. The apparatus may occupy a large laboratory, but the decisive atomic journey happens in a very small space. A fast muon can experience time dilation while it is moving through the beamline. From the laboratory's point of view, its lifetime becomes slightly longer because of relativity. This helps high-energy muons travel farther than a simple calculation using their rest lifetime would suggest. After a positive muon slows and forms ordinary low-energy muonium, the relativistic extension is usually small. The atom then lives on a timescale close to the familiar 2.2 millionths of a second. Binding the positive muon to an electron changes its energy slightly, but it does not meaningfully rescue it from weak decay. The binding energy is tiny compared with the energy associated with the muon's mass. The main decay remains available, and the lifetime of muonium is extremely close to the lifetime of a free positive muon. The situation differs from that of a negative muon stopped in matter. A negative muon can be captured by an atomic nucleus, giving it an additional way to disappear besides ordinary decay. The positive muon is repelled by positive nuclei and does not undergo the same nuclear capture. This is one reason positive muons are especially convenient for precision lifetime measurements and for muonium experiments. The positive muon lifetime has been measured so precisely that it helps determine the strength of the weak interaction. The decay rate is closely connected to a fundamental quantity known as the Fermi constant. By collecting enormous numbers of muon decays and controlling timing effects, physicists can extract that constant with very high precision. Muonium experiments usually have a different immediate goal, but they benefit from the same predictable decay. They may be measuring an atomic transition, a magnetic interaction, a chemical reaction, or the movement of a hydrogen-like species through a material. In every case, the known lifetime shapes the expected time distribution. The positron energy is not always the same because the decay produces 3 particles. The available energy is shared among the positron and the 2 neutrinos in many possible ways. Some positrons emerge with relatively low energy, while others carry much more. Detectors are designed to record an appropriate part of this range and to distinguish real decay events from background radiation and unrelated particles. Because neutrinos escape, the full decay cannot usually be reconstructed event by event in a small muonium experiment. Researchers do not need to reconstruct it. Their primary information comes from the positron's arrival time and direction. The invisible particles complete the physical process, while the visible one serves as the messenger. There is a useful quietness in the fact that the decay is so dependable statistically. The atom may be exotic, the apparatus may be complicated, and the quantum states may require advanced calculations, but the basic time pattern is consistent. Each group of newly formed atoms begins to disappear in the same characteristic way. That regularity allows researchers to compare one experimental condition with another. Suppose a microwave field is switched on at the frequency that changes the spin state of muonium. The altered spin behavior changes the pattern of detected positrons. Researchers repeat the measurement with the microwave frequency adjusted slightly higher or lower. The muon lifetime remains the same in every case, providing the falling background against which the resonance appears. A laser experiment follows a related strategy. Light tuned near an atomic transition changes how many atoms reach a selected excited state, or how they are later ionized. The resulting positron events are grouped by timing and laser frequency. The short lifetime limits the number of interactions, but it also provides a precise start and end structure for the measurement. The atom's instability even helps reduce certain backgrounds. A genuine muonium-related signal should appear within a few muon lifetimes after the beam arrives. Events occurring much later are less likely to come from the original atoms. Researchers can restrict the analysis to a suitable time window and reject signals that do not follow the expected timing. That does not make the analysis effortless. Electronic detectors can have dead times after recording an event. Closely spaced signals may overlap. A powerful pulse beam can produce a sudden burst of background. Magnetic fields may vary across the target. Muons may stop in parts of the apparatus other than the intended material. Each of these effects can imitate or distort the time pattern. Precision work therefore depends on understanding not only the atom, but the complete experimental clock. Cable lengths introduce delays. Detector responses take finite time. Data systems must decide which incoming muon belongs with which outgoing positron. Calibration signals check whether the measured intervals remain accurate. A millionth of a second is brief, but modern electronics divide it into many smaller timing bins. For the person listening to the result, it may sound as though scientists simply observed Muonium for 2 millionths of a second. In practice, no one watches a single atom continuously from formation to decay. The experiment records fragments of information from a vast collection of atoms. One event contributes an arrival time, another contributes a positron direction. Millions together reveal the atomic behavior. This is common in the microscopic world. Knowledge does not always come from following one object like a character in a story. It comes from repeated preparations and statistical patterns. The individual muonium atom remains private about exactly when it will disappear. The population is far more talkative. Its short life also changes what it means to store the atom. Ordinary atoms can be trapped for long periods, cooled, moved, and examined repeatedly. Muonium cannot be placed in a bottle for tomorrow. A source must keep producing fresh atoms while the experiment runs. The measurement is less like inspecting a permanent collection and more like studying a stream. Every atom enters, behaves, and vanishes. The apparatus does not mourn the loss. It records the positron, resets its timing, and waits for the next muon. Over hours or days, the experiment may observe billions of these brief lives. The final precision comes from abundance rather than endurance. The phrase brief life can also create the wrong impression that muonium spends most of its time merely waiting to decay. From the atom's point of view, if that phrase can be used carefully, there is no empty pause. Its quantum state evolves continuously. The electron and muon spins interact. External fields act on their magnetic moments. Collisions and radiation can change the state. The atom is available for measurement throughout the interval. 2 millionths of a second is only short when compared with human timing. Compared with many atomic and electromagnetic processes, it is an extended opportunity. The central challenge is not that physics has no time to happen. The challenge is that researchers must prepare the system, apply the intended interaction, and detect the result before the population becomes too small. That pressure has encouraged experimental designs that are fast, compact, and synchronized. It has also made the decay positron an essential part of nearly every method. The same event that destroys the atom supplies the information needed to understand it. By reading the timing and direction of those positrons, scientists can listen to the spin behavior of an atom that no longer exists. They can identify transitions, measure frequencies, compare magnetic responses, and test whether the predictions of quantum theory match the patterns left behind. The lifetime sets the limit, but it also gives the measurement its clock, and that clock leads directly into the precise ways researchers examine a vanishing atom. That clock leads directly to the way physicists study muonium. The atom cannot be collected and examined later, so every measurement must happen while it is forming, moving, changing state, and approaching the decay of its positive muon. Researchers do not listen to it in the ordinary sense. There is no microphone small enough, and even if there were, the atom would have very little to say in air. They listen by applying carefully chosen light or microwave radiation and watching how the probability of muon decay changes afterward. This method is called spectroscopy. At its simplest, spectroscopy asks how much energy an atom can absorb or release. An atom does not accept every possible amount. Its electron and positive muon can occupy only certain allowed quantum states. Moving from one state to another requires a particular energy difference. Radiation with the wrong frequency passes through or produces very little effect. Radiation with the right frequency can drive a transition. The result resembles tuning a radio, although the apparatus is considerably more expensive, and the station disappears after about 2/millionths of a second. The researchers adjust a frequency, repeat the experiment many times and count the decay positrons. They then adjust the frequency again. When the radiation matches an atomic transition, the pattern in the detectors changes. A resonance appears, and the position of that resonance tells them the energy difference between the states. This is how a vanishing atom becomes measurable. No one needs to keep the same atom alive long enough to explore every setting. Fresh muonium atoms are produced continuously, or in repeated pulses. One group encounters one frequency, another group encounters a slightly different frequency, and the accumulated results reveal where the transition lies. The measurement belongs to the population, not to any single atom. Muonium is unusually valuable for this work because its two constituents appear to be elementary. In ordinary hydrogen, the proton has an internal structure made from quarks and gluons. That structure causes small shifts in the atomic spectrum. Those shifts are interesting, but they complicate a test of the electromagnetic theory itself. In muonium, there is no proton and no conventional nucleus. The positive muon and electron behave as point-like leptons at the scales reached by current experiments. The theory used to describe their electromagnetic interaction is quantum electrodynamics. It is one of the most accurately tested theories in science. It explains how charged particles interact through the quantum electromagnetic field and how light participates in those interactions. The simple classroom picture says that opposite charges attract. Quantum electrodynamics keeps that basic result, but adds layers of corrections caused by the fluctuating field surrounding the particles. Even empty space is not treated as completely empty. Quantum fields can fluctuate. Brief intermediate processes can influence the energy of the atom. The electron can interact with its own electromagnetic field. The electron and muon can exchange virtual photons. Short-lived particle and antiparticle effects can alter how the electric interaction behaves. The motion of the electron can require relativistic corrections. The motion of the positive muon also matters because it is much lighter than a proton and cannot be treated as perfectly fixed. Each contribution is small, and some are extremely small. Together they determine the precise locations of the muonium energy levels. The calculation is not simply a polished version of the attraction between two charges. It is an accounting exercise in which nature has placed important information several decimal places beyond where ordinary instruments would stop looking. One of the clearest signals comes from the hyperfine structure of the ground state. The electron has spin and a magnetic moment. The positive muon also has spin and a magnetic moment. Their magnetic interaction divides the lowest atomic state into slightly different energy arrangements. In one arrangement, the spins are aligned in a shared way. In another, their total alignment is different. Microwave radiation can move the atom between these arrangements. A microwave field produces an oscillating magnetic influence. When its frequency matches the hyperfine energy difference, it changes the spin state more efficiently. Since the direction of the emitted positron depends on the muon spin, the transition changes the detector pattern. The apparatus therefore turns an invisible internal rearrangement into a countable signal. Muonium forms in a gas or another suitable target. A magnetic field sets the conditions. Microwaves fill a cavity around the atoms. Positron detectors surround the region. The frequency is scanned, and the resonance is reconstructed from many decays. The ground state hyperfine splitting corresponds to a frequency of about 4.463 billion cycles per second. Giving the number is easier than appreciating what it represents. It is not the electron physically circling the muon that many times. It is the frequency of radiation associated with the energy difference between two quantum spin arrangements. Measuring that frequency tests the calculation of the spin interaction. It also gives information about the magnetic moment of the muon. The magnetic moment describes how strongly the muon responds to a magnetic field. That quantity is important far beyond muonium because it enters other precision studies of the muon, including measurements of its anomalous magnetic behavior. A resonance can be shifted by the environment, so the experiment must understand the gas pressure, temperature, magnetic field, microwave power, and geometry of the target. Collisions between muonium and surrounding gas atoms can move the apparent transition frequency. Researchers repeat the measurement at different pressures and determine what the value would be without those collisions. Magnetic fields create another challenge. If the field is not the same throughout the region, atoms in different places experience slightly different transition conditions. The field must be mapped and monitored. Metal components can distort it. Temperature changes can alter equipment. A cable that seems entirely innocent can become a small contributor to uncertainty, which is a familiar laboratory talent of cables. Microwave power also requires care. Too little power produces a weak transition and poor statistics. Too much can broaden or shift the resonance. The atoms remain in the interaction region for different lengths of time because they move at different speeds and decay randomly. The measured line is therefore shaped by the atomic physics, the beam timing, and the design of the cavity. The museum experiment at the Japan Proton Accelerator Research Complex has demonstrated hyperfine spectroscopy using an intense pulsed muon beam. Its measurements near zero magnetic field agreed with earlier results and with quantum electrodynamics. The purpose of increasing the muon intensity and improving the detectors is not merely to repeat a known number with more digits. Greater precision makes the comparison more sensitive to small missing effects. Another major test uses the transition between the lowest energy state and the first long-lived excited state. These are commonly called the 1s and 2s states. The notation is useful in technical work, but the physical idea is straightforward. The electron begins in the lowest allowed arrangement around the positive muon and absorbs energy that places it in a higher arrangement. The energy gap is much larger than the hyperfine splitting, so lasers rather than microwaves are used. In a well-known method, the atom absorbs two photons whose combined energy matches the transition. The photons travel in opposite directions. This arrangement helps cancel the first-order Doppler shift caused by the motion of the atom. The Doppler effect is familiar from a passing siren. Motion changes the frequency received by an observer. The same problem appears in atomic spectroscopy. Muonium atoms move through the laser beams, and atoms travelling toward the light see a slightly different frequency from atoms travelling away. Using two opposite photons greatly reduces the leading motion-related shift, allowing a narrower and more accurate measurement. The 1s to 2s transition is especially valuable because it depends strongly on the relative masses of the electron and muon. Once the frequency is measured and the theory is supplied, researchers can determine the muon to electron mass ratio. This is another example of spectroscopy turning a frequency into a statement about a fundamental particle. The best established measurement agrees with the prediction from quantum electrodynamics, but modern projects aim to improve the precision greatly. The Muon experiment at the Paul Scherrer Institute is developing methods to produce slow muonium in vacuum and excite the 1s to 2s transition with highly controlled laser light. Slower atoms reduce transit effects and spend longer in the laser region. Precision laser work brings its own collection of complications. The laser frequency must be known accurately. Its pulses must arrive when muonium is present. The light intensity can shift the transition. The atoms have a distribution of speeds. Some collide with surfaces, others decay before reaching the useful region. The laser beam is not perfectly uniform, and the target does not emit every atom from exactly the same location. A frequency comb can provide a precise optical reference. Despite the name, it is not used to improve the hairstyle of the laboratory. It produces a set of sharply defined light frequencies that allow the spectroscopy laser to be measured against a stable standard. This connects the atomic transition to modern time and frequency measurement. Researchers also study smaller separations among excited states. One famous example is the Lamb shift. A simpler relativistic theory would predict that certain atomic states have the same energy. Quantum electrodynamics shows that interactions with the quantum field separate them slightly. The shift was first recognized in hydrogen and became an important clue in the development of modern quantum field theory. Muonium has its own Lamb shift. Measuring it tests corrections involving the electron, the muon, their recoil, and the quantum vacuum without the uncertain internal structure of a proton. Recent microwave spectroscopy of excited muonium improved the measurement substantially and found agreement with the theoretical calculation. The excited state needed for this work is difficult to prepare. Most newly formed muonium begins in the ground state. Researchers can create a smaller population in a metastable excited state, meaning a state that lasts longer than many ordinary excited states. Microwave radiation then drives a transition to a nearby state that decays rapidly. The change can be detected through the particles or photons produced afterward and through the timing of the muon decay. The word metastable may sound reassuring, but the entire atom is still limited by the muon lifetime. It only means that the excited electron arrangement does not immediately drop to the ground state. In Muonium physics, stability is often a comparison between one very short time and another that is even shorter. Measurements of the hyperfine splitting, the 1s to 2s transition, and the Lamb shift probe different parts of the same theory. The hyperfine splitting is especially sensitive to the magnetic interaction and the muon magnetic moment. The 1s to 2s interval is especially useful for the muon mass. The Lamb shift examines quantum field corrections and recoil effects. Agreement across all of them is more powerful than agreement in only one place. A theory can sometimes match one result because an uncertain input value has been adjusted. It becomes harder to imitate success when several independent measurements depend on the inputs in different ways. Muonium gives physicists a small network of linked tests. The mass obtained from one transition can be used in the prediction of another. The magnetic moment obtained from hyperfine spectroscopy can be compared with values used elsewhere. The calculations also reveal which uncertainties matter most. At some levels of precision, the experimental measurement is the main limitation. At others, the uncertainty in the muon mass or magnetic moment limits the theoretical prediction. Improving one measurement can therefore sharpen several tests at once. This is one reason fundamental constants are not simply numbers printed permanently in the back of a textbook. They are measured quantities with uncertainties and relationships. A better muonium frequency can improve the known muon mass. That improved mass can sharpen another quantum electrodynamics calculation. The new prediction can then be compared with a different experiment. Physicists are also alert to the possibility that an unknown force could shift the muonium spectrum. A new particle that interacts weakly with electrons and muons might add a tiny extra attraction or repulsion. The effect could depend on distance, spin, or the identities of the particles. If large enough, it would move one or more transition frequencies away from the standard prediction. No confirmed shift of that kind has appeared in muonium spectroscopy. The agreement with quantum electrodynamics instead places limits on possible new interactions. A null result is not an empty result. It says that any proposed force affecting the atom must be weaker than the experiment could have detected, or must have properties that avoid the particular measurement. Muonium is especially useful for testing interactions involving muons because ordinary atoms contain electrons but no muons. A new force that prefers heavier leptons could be nearly invisible in conventional atomic spectroscopy. Placing a muon inside an atom creates a controlled system in which such an interaction may affect the energy levels. Some analyses use muonium measurements to constrain possible violations of Lorentz symmetry or the combined symmetry involving charge, spatial reflection, and time reversal. These ideas concern whether the laws of physics remain exactly the same under fundamental changes of viewpoint and particle identity. The experiments do not require a dramatic breakdown. They search for tiny frequency changes that might depend on the orientation of the apparatus, the time of day, or the state of the particles. If the resonance frequency changed as Earth rotated, for example, that could suggest that the atom was responding to a preferred direction in space. Researchers look for such variations while accounting for ordinary changes in the laboratory. Temperature cycles, magnetic drift, beam intensity, and equipment stability must be understood before a daily pattern can be treated as fundamental physics. The patience involved is easy to underestimate. A resonance may require many hours of data at different settings. A possible shift can be smaller than the width of the observed line. Statistical analysis estimates the center, while systematic studies test how the answer changes when assumptions or conditions are varied. The final result may be one number, but that number stands on a large structure of calibrations and cross-checks. The phrase, "listening to an atom," is therefore more literal than it first appears, provided listening is understood as finding the frequency at which the atom responds. The apparatus sends a controlled note. Muonium either responds strongly or weakly. Its decay positron carries the answer. Repeating the exchange builds a spectrum. Unlike a normal musical instrument, the atom does not have imperfections from construction. Every muonium atom in the same state is governed by the same particle properties. The imperfections belong mostly to production, motion, fields, collisions, and detection. This repeatability is what makes atomic spectroscopy such a precise form of measurement. Muonium adds one more advantage. Since there is no extended nucleus, theory and experiment can meet without the same nuclear uncertainties found in hydrogen. The positive muon still recoils. It still has a magnetic moment. It still decays. Those are not complications to be removed. They are known parts of the system, and often the very properties being measured. The atom vanishes before any person could consciously notice its presence, yet the resonance frequencies can be determined through millions of repeated lives. Each event contributes a small piece of evidence. Together they test calculations that include the effects of relativity, quantum fields, particle recoil, magnetic interactions, and the restless behaviour of what we casually call empty space. All of this precision rests on a basic fact that once sounded contradictory. The electron and positive muon remain together long enough to behave as an atom. One is matter and the other is antimatter, but they do not annihilate each other. Spectroscopy depends on that survival. The next step is to look directly at why their shared atom is allowed to exist, what annihilation actually requires, and how matter can hold antimatter without the immediate flash that popular explanations often lead us to expect. What annihilation actually requires is more specific than the usual phrase matter meets antimatter. Popular explanations often make annihilation sound automatic. Put any particle of matter beside any particle of antimatter, and both disappear in a flash. That picture is memorable, but it leaves out the identities of the particles involved. Muonium survives because an electron and a positive muon are not exact opposites of each other. The electron is a matter particle. Its matching antiparticle is the positron. A positron has the same mass and spin as an electron, but the opposite electric charge and the opposite particle identity. When an electron meets a positron under suitable conditions, they can annihilate through the electromagnetic interaction. Their mass and motion are converted into other particles, often photons. A bound electron and positron can even form a short-lived atom called positronium before the annihilation occurs. The positive muon is not a positron. It is the antiparticle of the negative muon. A negative muon has the same negative charge as an electron, but it belongs to the muon branch of the lepton family and has much more mass. Its positive antiparticle carries positive charge and the corresponding antimatter identity. Placing a positive muon beside an electron therefore brings together two different kinds of lepton. One is ordinary electron matter, the other is muon antimatter. Opposite electric charges attract without asking whether the particles belong to the same generation. Electromagnetism sees one negative charge and one positive charge, so it allows them to form a bound state. Annihilation into photons is much more selective. The electromagnetic interaction preserves the kind of charged lepton involved. It does not normally turn an electron and a positive muon into a set of photons, because the electron identity and the antimuon identity would have nowhere to go. This is the central reason muonium does not instantly disappear. Its two constituents have opposite charges, which lets them bind, but they are not a particle and its own antiparticle, which prevents the rapid electromagnetic annihilation familiar from positronium. The same electrical attraction that holds hydrogen together can hold muonium together, while the mismatch of particle identities protects the atom from the fastest destructive route. It helps to separate electric charge from particle identity. Electric charge tells us how a particle responds to the electromagnetic field. An electron and a negative muon carry the same amount of negative charge. A positron and a positive muon carry the same amount of positive charge. That does not make the electron and negative muon the same particle, or the positron and positive muon the same antiparticle. A familiar comparison would be two keys made from the same metal. They may have the same weight and colour, but only one fits a particular lock. Charge is one property. Mass, lifetime, flavour and other quantum properties provide more information. Annihilation depends on the complete set, not merely on whether one charge is positive and the other is negative. The word flavour is used in particle physics to distinguish related particles such as the electron, muon and tau. It sounds as though the standard model was assembled in a kitchen, but it simply labels different members of the lepton family. The electron has electron flavour. The muon has muon flavour. Their neutrinos carry corresponding identities. The positive muon carries the antimatter version of muon flavour. In ordinary electromagnetic processes, these flavours are preserved. An electron can emit or absorb a photon and remain an electron. A muon can do the same and remain a muon. An electron and positron can annihilate because their electron identities cancel. A negative muon and positive muon can annihilate because their muon identities cancel. An electron and positive muon do not provide the same cancellation. Muonium can therefore sit in a state that is both mixed and balanced. It is mixed because one constituent is matter and the other is antimatter. It is balanced because their electric charges cancel. It is not balanced in the sense of containing an electron beside an anti-electron or a muon beside an anti-muon. The atom has no direct pair available for rapid electromagnetic annihilation. This also explains why the word antimatter should not be treated as a single substance. Antimatter comes in different particle species just as matter does. A positron, an antiproton, and a positive muon are all antimatter particles, but they are not interchangeable. Each is the partner of a specific matter particle. Saying that a positive muon is antimatter tells us something important, but it does not erase the fact that it is a muon. If a positron entered muonium and encountered the electron, those two could annihilate. If a negative muon encountered the positive muon, that matching pair could also annihilate. The original two constituents do not have either relationship. They can remain bound until something else interrupts them. The most common interruption is still the ordinary decay of the positive muon. Through the weak interaction, the positive muon changes into a positron and two neutrinos. Once that happens, the positive centre of the atom is gone. The electron is left behind and muonium no longer exists. The atom ends because one constituent decays, not because its matter and antimatter components destroy each other. The electron does not cause that decay. A free positive muon follows almost the same process with almost the same average lifetime. Binding it to an electron changes the situation only slightly because the atomic binding energy is tiny compared with the mass energy involved in muon decay. The electron is present, but the weak interaction inside the muon continues with little concern for the new domestic arrangement. There is, however, a subtle correction to the simple statement that the electron and positive muon cannot annihilate. They cannot undergo the fast electromagnetic annihilation of a matching particle and antiparticle pair. The weak interaction does allow an electron and a positive muon to disappear together into neutrinos. This process is a genuine annihilation of the bound constituents, but it is extraordinarily rare. In that rare route, the electron and positive muon are replaced by an electron neutrino and a muon antineutrino. Electric charge is conserved because the initial charges add to zero and the final neutrinos are neutral. The electron and muon family identities are also carried away by the corresponding neutrinos. Nothing is lost from the bookkeeping. The interaction simply uses the weak force rather than electromagnetism. The predicted probability is tiny compared with ordinary muon decay. Only several such invisible annihilations are expected for every trillion ordinary muonium decays. The final neutrinos would pass through the surrounding detectors almost every time, so the event would appear as missing energy. The atom would enter the apparatus and no positron or other ordinary visible decay product would emerge. Calling this an invisible decay does not mean the atom quietly slips into another dimension. It means the final particles are neutrinos, which rarely interact with the detector. Researchers would infer the process from the absence of the usual visible signal, and from careful control of every ordinary way that energy could escape unnoticed. This rare process does not threaten the practical stability of muonium. The positive muon is overwhelmingly more likely to undergo its normal decay before the electron and muon annihilate into neutrinos. The atom still survives for about the lifetime of the muon. Weak annihilation is important as a theoretical possibility and a potential test of new physics, not as the everyday ending of Muonium in the laboratory. The contrast with positronium is useful. Positronium consists of an electron and a positron. Their masses are equal, their charges are opposite, and their particle identities are exact opposites. They bind because of electromagnetic attraction, but the same matching relationship lets them annihilate electromagnetically. Depending on the spin state, positronium usually survives for only a tiny fraction of the positive muon lifetime. Muonium has a similar atomic size because the electron is still bound to a positive charge. Its lifetime is far longer than that of positronium because the electron and positive muon cannot use the rapid photon-producing annihilation channel. Muonium waits for the muon to decay through the weak interaction, which is much slower than a typical electromagnetic process. The strength of the interaction matters greatly. Electromagnetic changes usually happen faster than weak changes at these energy scales. That is why an excited atom can release light quickly, while a muon can remain present for a few millionths of a second before decaying. The weak interaction is not feeble in every possible circumstance, but for low-energy muonium it provides a much slower clock. The electron and positive muon are still extremely close by everyday standards. In the lowest atomic state, the electron probability is concentrated over a region similar in size to a hydrogen atom. The particles do not avoid each other. Their quantum wave functions overlap, and the electron can be found very near the positive muon. Survival is not caused by keeping matter and antimatter physically separated. This point is worth lingering on because it corrects a common intuition. Muonium does not survive by placing a barrier between its constituents. There is no microscopic wall, no repulsive shell, and no rule saying that they must remain on opposite sides of the atom. They are bound precisely because they interact and occupy the same atomic system. What protects them is the mismatch of their full quantum identities. The word contact also becomes unreliable at this scale. Particles described by quantum fields are not hard beads with polished surfaces. Annihilation probability depends on the allowed interaction and on the overlap of the quantum state. Even perfect overlap does not create a forbidden electromagnetic process. The particles need both proximity and a permitted way to transform. Conservation laws decide which transformations are allowed. Electric charge must balance. Energy and momentum must balance. Angular momentum must balance. The relevant particle identities must also be carried through the interaction according to the rules of the theory. A possible final state must satisfy all of these conditions at once. Photons have no electric charge and no electron or muon flavor. An electron and positron begin with opposite electron identities, so those identities cancel, and photons are allowed. A negative muon and positive muon begin with opposite muon identities, so they can do the same. An electron and positive muon begin with electron identity and anti-muon identity. Turning them only into photons would discard both. The weak interaction offers neutrinos that can carry those identities onward. That is why the rare invisible annihilation is allowed while rapid annihilation into photons is not. The distinction is not a special rule invented to save muonium. It follows from the same standard model structure that governs muon decay, neutrino production, and many other particle processes. Nature does allow some lepton flavors to mix through neutrinos. Neutrinos produced with one flavor can later be detected with another after traveling through space. This discovery showed that the separate flavor labels are not absolutely conserved in every circumstance. Even so, charged lepton flavor-changing processes remain extraordinarily suppressed in the standard model. Muonium is sensitive to that suppression. If an unknown interaction connected electrons and muons more strongly than expected, it could change how the atom behaves. It might create new decay routes, shift energy levels, or allow muonium to turn into antimuonium. Antimuonium would contain a negative muon and a positron. It is the charge-reversed counterpart of muonium. A spontaneous conversion would change both constituents at once. The electron would become a positron, and the positive muon would become a negative muon. The total electric charge would remain zero, but the lepton family assignments would reverse. The standard model with no neutrino masses permits such conversion only at an immeasurably small rate. Many proposed extensions of particle physics can make it larger. Researchers therefore search for the unmistakable signs of antimuonium appearing after muonium was created. Failure to see the conversion places limits on those proposed interactions. This future possibility does not mean ordinary muonium is secretly switching back and forth at an observable rate. Under known physics, it remains muonium throughout its short life. The conversion search matters because a positive result would show that electron and muon identities can change through a new process far stronger than the standard model predicts. The stability of muonium also has a useful chemical consequence. The atom lives long enough to collide and react before the muon decays. In gases and organic materials, it can attach to molecules and create short-lived radicals. Those reactions would not be possible if the electron and positive muon annihilated as quickly as an electron and positron do in positronium. Muonium can substitute for hydrogen because the electron sees a positive central charge. When it approaches a molecule, its electron can participate in bonding. The positive muon acts as a very light hydrogen nucleus. The matter and antimatter label remains correct, but chemistry responds mainly to charge, mass, and electronic arrangement. This is another reminder that antimatter does not behave as a supernatural contaminant. A positive muon follows the same electromagnetic laws as any other positively charged particle. It can slow in matter, capture an electron, form an atom, and participate in chemical reactions. Its antimatter identity becomes decisive only in processes where the matching particle relationships and conservation rules matter. An antiproton can bind with a positron to make antihydrogen. That atom is entirely antimatter. and it does not annihilate internally because the antiproton and positron are not antiparticles of each other. They have opposite charges and different particle identities, just as the proton and electron do in hydrogen. Antihydrogen annihilates when it encounters ordinary matter, not simply because it contains two kinds of antimatter. Muonium is stranger because it combines matter and antimatter within the same atom. Yet the underlying rule is the same. Internal annihilation is not triggered by the labels matter and antimatter alone. It requires the correct partners and an allowed final state. There are other mixed systems in which an ordinary particle binds to an antiparticle of a different species. Their lifetimes depend on which interactions are available. Some disappear quickly through strong interactions. Others survive long enough for atomic behavior to be measured. The phrase exotic atom covers a varied group, and each member follows its own particle bookkeeping. Muonium occupies an unusually clean position in that group. Both constituents are leptons, so the strong nuclear interaction does not complicate the binding. Electromagnetism creates the atom. The weak interaction eventually removes the muon. The separation between those roles makes the system easier to calculate than many other matter and antimatter combinations. This clean structure is also why physicists do not treat muonium merely as a curiosity. It demonstrates in the most direct way that matter and antimatter can form an organized bound system when the particle identities permit it. The atom is not a temporary truce between enemies. The electron and positive muon are following ordinary quantum rules from the moment they bind until the muon decays. The energy released in a possible annihilation is not waiting like pressure behind a door. Mass energy is a property of the particles, but it can be converted only through allowed interactions. A match does not light merely because chemical energy exists in the match head. The physical conditions and reaction pathway must be present. Muonium lacks the fast electromagnetic pathway that would turn its constituents into photons. The atom can still be destroyed in more ordinary ways. A collision may remove the electron and leave a bare positive muon. Another particle may exchange charge with it. Muonium can react chemically and become part of a molecule. It can strike a surface and lose its recognizable atomic state. None of those events is the dramatic mutual annihilation suggested by its mixed composition. If the muonium is ionized, the positive muon continues until it decays. If the electron is transferred to another atom, it continues as an electron in its new environment. Their separation does not release a hidden explosion. The binding energy involved is comparable to ordinary atomic energies, not to the complete conversion of the particle masses. When the positive muon finally decays, a positron appears. That positron is a true antiparticle of an electron. It may later encounter an electron in the surrounding material and annihilate, often producing photons. This later annihilation can happen after muonium itself has already ended. It involves the decay positron and an environmental electron, not the original positive muon and its bound electron. The sequence is easy to confuse. First, a positive muon binds an electron and forms muonium. Next, in the overwhelmingly common route, the positive muon decays into a positron and neutrinos. The original electron is released. Later, the positron slows down and may annihilate with some electron in the material. Matter and antimatter annihilation does occur, but it is a later event involving a different pair. Detectors in muonium experiments are usually designed to notice the energetic positron soon after the muon decay, before following every later interaction. That positron reveals the muon spin direction and helps reconstruct what the atom was doing. The eventual annihilation photons may contribute background or additional detector signals, depending on the apparatus. A listener might reasonably ask whether the original electron could annihilate with the newly created positron. It can, if their paths bring them together after the muon decay. They are now a matching pair. There is no guarantee that they will meet, because the positron often leaves with high energy, while the electron remains near the original site or joins the material. The important point is that the permitted matching pair exists only after the positive muon has changed into a positron. Before decay, muonium is protected by identity. After decay, the atom is gone, and a different set of possibilities begins. The rules never change. The list of particles changes, so the allowed interactions change with it. This careful distinction also protects us from a broader misunderstanding about the early universe. The disappearance of antimatter from the visible cosmos is not explained by saying that every matter particle annihilated with any antimatter particle nearby. Specific particles met their matching antiparticles through allowed processes. A slight excess of matter appears to have remained, but the origin of that excess is still unresolved. Muonium does not solve that cosmic puzzle on its own. It gives physicists a controlled place to test whether electrons and muons obey expected symmetries, and whether unknown interactions connect their identities. Its mixed composition makes it sensitive to processes that ordinary hydrogen cannot test in the same way. For the few millionths of a second before the positive muon decays, matter really does hold antimatter in a stable atomic arrangement. Stable here means stable against rapid annihilation, not permanent. The electron remains bound because of electric attraction. The positive muon remains present until the weak interaction changes it. The atom follows well-defined energy levels and responds to radiation like the hydrogen relative it is. There is no contradiction once the labels are made precise. Antimatter is not automatically destructive to every kind of matter. Electric attraction does not guarantee annihilation. Physical closeness does not override conservation laws. A transformation occurs only when the initial particles, the interaction, and the possible final particles all fit the same set of rules. Muonium fits the rules for an atom remarkably well. It also fits a much rarer set of rules that could make it disappear invisibly into neutrinos. It may even be sensitive to unknown rules that would turn it into antimuonium. Those possibilities take us from the simple question of why it survives to a more demanding one. If muonium could cross the antimatter mirror and return with every charge reversed, what would that tell us about the laws that separate the particle families? The rules that protect muonium from immediate annihilation leave open a much stranger possibility. The atom might not have to remain muonium for its entire brief life. Under the right unknown interaction, the electron could become a positron, while the positive muon became a negative muon. The neutral atom would still contain two particles. Its total electric charge would still be zero. From the outside, it would still resemble a light hydrogen-like system. Inside, however, every matter and antimatter role would have been reversed. The new atom is called antimuonium. Muonium contains a positive muon and an electron. Antimuonium contains a negative muon and a positron. The masses of the two atoms should be the same. Their charges cancel in the same way. Their atomic energy structures should closely mirror each other. The difference lies in particle identity. Muonium combines an antimatter muon with a matter electron. Antimuonium combines a matter muon with an antimatter electron. No ordinary collision needs to knock the two particles out and replace them one at a time. The proposed process is a direct quantum conversion of the whole-bound system. Muonium would begin as itself, develop a small antimuonium component, and perhaps be found in the reverse state before the muon decays. Physicists often describe this as mixing or oscillation. The word oscillation may suggest that the atom repeatedly flips back and forth like a light switch being operated by a very indecisive person. Quantum behavior is less mechanical. If a new interaction connects the two atomic states, a system prepared as muonium does not remain a perfectly pure muonium state as time passes. Its quantum state becomes a combination of the original atom and a possible antimuonium atom. A measurement can then find one identity or the other. This is related in spirit to several other forms of particle mixing. Certain neutral mesons can change into their antiparticles. Neutrinos created with one flavor can later be detected with another. These systems are not secretly swapping name tags in flight. Their quantum states evolve because the states produced in an interaction are not always the same as the states that move with definite energies. Muonium and antimuonium would provide an especially clean version of the idea. Both are electrically neutral, so a conversion would not violate electric charge conservation. Their masses are expected to match, so the process does not require the atom to find a large supply of energy. The difficulty is not charge or energy. The difficulty is lepton identity. A useful bookkeeping system assigns electron family number to electrons and their neutrinos, and muon family number to muons and their neutrinos. Antiparticles carry the corresponding opposite assignments. Ordinary muonium begins with 1 unit of electron family identity and 1 unit of antimatter muon identity. Antimuonium has exactly the reverse. A conversion changes the separate electron and muon family numbers by 2 units. In the original standard model with massless neutrinos that change is forbidden, the electron and muon families remain separate in the relevant interactions. The later discovery of neutrino oscillations showed that nature does not preserve flavour in such a simple, absolute way. Neutrinos have mass, and the flavour in which a neutrino is produced is a mixture of different mass states. That discovery makes the statement forbidden by the standard model require a little care. The minimal theory as first written does not allow the conversion. A modern extension that includes the known neutrino masses and mixing can generate it in principle. The predicted effect is so heavily suppressed that no foreseeable muonium experiment is expected to see it. For practical purposes, an observable conversion would still be evidence for physics beyond the known explanation. The suppression comes from several sources. The interaction would have to connect the electron and muon families through intermediate quantum processes. Contributions from different neutrino states tend to cancel. The neutrino masses are extremely small compared with the particles involved in the weak interaction. The remaining conversion effect becomes tiny, and the probability becomes far below the sensitivity of present or planned experiments. This is why the search is so appealing. Many measurements test whether a known process occurs at exactly the expected rate. Muonium to antimuonium conversion searches for a process that should be essentially absent. The standard model background is not merely small in the ordinary experimental sense. The expected conversion from known neutrino physics is so remote that a convincing observation would be difficult to explain as a slight correction to familiar theory. A new interaction could change that conclusion. Some theories introduce particles that connect 2 charged leptons directly. Others include additional Higgs particles, heavy neutrinos, new force-carrying particles, or interactions that violate the usual lepton family rules. Certain models contain particles with 2 units of electric charge. Such a particle could link 2 same sign-charged leptons in a way the familiar force carriers do not. Muonium conversion does not select one model in advance. It asks a general experimental question. Can a positive muon and electron-bound state become a negative muon and positron-bound state? Different theories predict different strengths, spin dependencies, and responses to magnetic fields. A measured rate could then help distinguish which kind of new interaction was responsible. Before dreaming about a discovery, the experiment must identify what antimuonium would actually look like. An ordinary muonium atom ends when its positive muon decays. That decay produces an energetic positron along with 2 neutrinos, while the original bound electron is left behind. Antimuonium reverses the visible charges. Its negative muon decays into an energetic electron and 2 neutrinos, while the bound positron remains as a slow atomic particle. That pair provides the basic signature. The detector looks for a high-energy electron from the negative muon decay, and a low-energy positron released from the same place at the same time. The energetic electron shows that a negative muon was present. The slow positron shows that the negative muon belonged to an antimuonium atom rather than arriving alone. The word slow is relative. The positron was bound with ordinary atomic energy, so it begins with far less motion than the energetic electron created in muon decay. It may be guided and accelerated by electric and magnetic fields toward a dedicated detector. After reaching matter, it can annihilate with an electron and produce photons, giving another recognizable signal. The energetic electron follows a curved path in a magnetic spectrometer, Its direction and momentum can be reconstructed from detector hits. The slow positron travels through a separate transport system designed for low-energy particles. The experiment then demands the correct timing and geometry. Both signals must point back to the same muonium decay region and appear within the expected interval after the incoming positive muon arrived. This coincidence requirement is powerful because many ordinary events can imitate one piece of the signal, but far fewer can imitate all of it. A random electron may cross the detector. A positron may arise from an unrelated interaction. Background radiation may produce photons. The challenge is to show that an energetic negative electron and a slow positive atomic particle were born together from a neutral atom that began as muonium. The best completed direct search was performed at the Paul Scherrer Institute. Positive muons entered a porous target where some formed muonium and escaped into vacuum. Vacuum was important because collisions in matter could destroy the atom, obscure its identity, or create backgrounds. The atoms were then allowed to travel through the observation region, while detectors waited for the antimuonium decay pattern. The apparatus surrounded the region with tracking chambers and other detectors for the energetic electron. An electrostatic system collected the slow positron and guided it toward a detector where its arrival and annihilation could be recorded. The event had to match the expected time, position, energy, and coincidence requirements. After collecting data, the researchers did not find an excess that could be identified as conversion. One event survived the selection in the final high-sensitivity search, but the expected number of accidental background events was larger than one. The event therefore did not provide evidence for antimuonium. It was compatible with unrelated signals happening to imitate the required pattern. The resulting upper limit remains the standard direct bound. Under the stated interaction assumptions and in the magnetic field used by the experiment, the probability was limited to fewer than about 8 events in 100 billion muonium atoms. Another way to hear that number is that the experiment found no evidence, even at roughly the level of one conversion in more than 10 billion opportunities. The limit is not a universal number independent of theory. Conversion can depend on the spin state of the atom and on the structure of the proposed new interaction. The magnetic field used to control and analyze the particles can shift muonium and antimuonium energy levels differently. If the two states no longer have matching energies, their mixing is reduced. This is similar to trying to transfer motion between two identical pendulums. If they swing at the same natural rate and are weakly connected, energy can pass between them efficiently. If one pendulum is altered so that its natural rate differs, the transfer becomes less effective. Muonium and antimuonium are quantum states rather than pendulums, but the shared lesson is that mixing is strongest when the connected states remain closely matched in energy. A magnetic field interacts with the electron, positron, and muon magnetic moments. It separates the spin energy levels and can suppress conversion for some possible interactions. Experiments cannot simply remove every field because fields are needed to guide particles and measure their motion. The design must balance conversion sensitivity against the practical need to control the charge decay products. Different theoretical interactions respond differently to the field. A result quoted for one assumed interaction may need a correction before it is applied to another. This is why experimental papers often provide both a direct probability limit under specified conditions and a limit on the effective strength of a proposed conversion interaction. The existing bound says that such an interaction must be much weaker than the ordinary weak interaction responsible for muon decay. It has already ruled out or restricted parts of many speculative models. A theory may have been designed to explain neutrino masses, dark matter, or another particle puzzle, only to discover that its new particles would also make muonium convert too often. The absence of conversion then trims the theory's allowed possibilities. This is one of the quiet strengths of precision experiments. They do not need to create a new heavy particle directly. A heavy particle that cannot be produced by the accelerator may still influence a low-energy atom through a brief intermediate process. the effect becomes weaker as the new particle becomes heavier or its interaction becomes smaller, but an extremely sensitive measurement can still set useful limits. A tiny atom at low energy can therefore test ideas associated with energy scales far beyond the atom itself. The muonium does not contain enough energy to manufacture the proposed heavy intermediary as a real particle. Quantum field theory allows that particle to affect the transition virtually. It appears as part of the interaction, rather than as a detectable object flying from the experiment. This does not mean that any unexplained event can be assigned to an invisible particle and declared a discovery. A real conversion signal would need to appear repeatedly, follow the expected time dependence, respond consistently to magnetic fields, and survive changes in the detector and analysis. Independent confirmation would be essential. Time dependence offers one of the clearest checks. Muonium is created at the beginning of the observation. If conversion is caused by mixing, the antimuonium probability begins at 0 and grows during the early part of the atom's life. At the same time, ordinary muon decay steadily removes atoms from the sample. The useful signal is shaped by a competition between the growth of the converted component and the falling number of surviving muons. Very early events have had little time to convert. Very late events are rare because most muons have already decayed. The best observation window lies between those extremes. A pulsed muon beam can help because the experiment knows when a group of atoms was created and can examine the decay products according to the delay after the pulse. The old experiment used the tools available at the time and established a limit that has remained unchallenged for decades. New facilities can provide more intense muon beams, improved porous targets, faster electronics, stronger background rejection, and better particle tracking. These advances have encouraged a new generation of proposals. The Muonium to antimuonium conversion experiment, known as MACE, has been designed to push the sensitivity more than 2 orders of magnitude beyond the existing direct limit. Its target is a conversion probability around 1 in 10 trillion. Reaching that level requires far more than increasing the beam intensity and hoping the answer becomes obvious. A stronger beam creates more muonium, but it can also create more accidental coincidences. If many particles arrive close together, an electron from one event may be mistakenly paired with a positron from another. Detectors must handle high rates without losing timing precision. The target must release a large fraction of muonium into vacuum. The transport system must collect slow positrons efficiently, while rejecting faster unwanted particles. The MACE design separates the main tasks. A magnetic spectrometer measures the energetic electron from negative muon decay. A momentum-selective transport system guides the slow positron away from the production region. A positron detector confirms its arrival and annihilation. Timing links the signals to the original incoming muon and to each other. The positron transport is particularly important because low-energy charged particles are easily disturbed. Electric fields can accelerate them, while magnetic fields guide their spiraling paths. The transport system can be arranged to accept the momentum range expected from an atomic positron and reject much of the background. Measuring the travel time adds another filter. No detector is perfectly silent. Cosmic rays pass through the apparatus. Natural radioactivity produces signals. Muons stop in unwanted materials. Electrons scatter from surfaces. Positrons can arise through ordinary processes. Simulations estimate these backgrounds. Prototype detectors test the estimates, and control measurements examine conditions where a true conversion signal should be absent. The target itself is a major part of the problem. A positive muon must stop, capture an electron, form muonium, and let the neutral atom escape into vacuum. If it forms too deep inside the material, it may decay before reaching the surface. Laser-structured aerogel and other porous materials can increase the useful emission rate by providing short routes into open space. Once in vacuum, the atom begins its brief opportunity to mix. A large open decay region gives it time, but making the region larger also changes detector acceptance and background. The geometry must be optimized around the muon lifetime. the atom's speed, and the possible time development of conversion. The experiment is therefore not merely a camera pointed at an atom. It is a timed sequence that prepares one identity and searches for the charge reverse decay of the other. Every component asks a different part of the same question. Was a positive muon delivered? Did muonium form? Did a negative muon later decay in the observation region? Was a slow positron released beside it? Did all signals belong to one event? Suppose that a future experiment observes a convincing excess. The first task would be to challenge it. Researchers would reverse fields, alter timing windows, change target conditions, and inspect every background source. A genuine conversion signal should behave according to a consistent quantum process. An electronic fault or accidental coincidence usually reveals itself by failing one of these tests. If the signal survived, its rate and magnetic field dependence could provide clues about the new interaction. Some theories predict scalar intermediary particles, which behave differently from vector intermediary particles. Others involve heavy neutrinos or particles carrying twice the usual unit of electric charge. The spin states most likely to convert would help narrow the possibilities. The result would also belong to a wider program of charged lepton flavor violation. Other experiments search for a muon decaying into an electron and a photon, a positive muon decaying into one electron and two positrons, or a negative muon changing into an electron near a nucleus without producing neutrinos. None of these processes has been confirmed. Muonium conversion tests a different combination of particle identities and can be sensitive to models that produce weak signals elsewhere. A theory may suppress ordinary muon decay channels while allowing the two particle-bound state to mix. Comparing several searches is therefore more informative than relying on only one. Neutrino physics adds another layer. The observed mixing of neutrino flavors proves that lepton flavor is not an exact symmetry of nature. It does not tell us how large charged lepton flavor violation should be in every process. In the simplest extension with tiny neutrino masses, the charge processes remain far too rare to detect. A muonium conversion signal would show that something more than known neutrino mixing connects the families. Recent theoretical work has also examined whether the conversion could help distinguish different possibilities for neutrino masses. Neutrinos may be distinct from their antiparticles, or they may be particles that are their own antiparticles. Some intermediate possibilities allow mostly ordinary behavior with a small splitting. These structures can affect the predicted muonium mixing, although the answers depend on the wider model. That makes the atom a possible probe of a question that seems unrelated to its appearance. Muonium contains no neutrino, yet neutrinos participate in the quantum processes that could connect it to antimuonium. The atom becomes sensitive to particles that pass unnoticed through almost every detector. For now, the antimatter mirror has not shown a reflected atom. Every measured muonium sample has behaved consistently with the known picture. The positive muon eventually decays, the electron is released, and no confirmed negative muon with a bound positron appears in its place. The absence is already useful. It tells us that any new interaction capable of reversing the atom must be weak, heavy, carefully hidden, or absent. Better experiments will make that hiding place smaller. They may find conversion, or they may push the limit down by another 100-fold and remove more speculative possibilities. Either outcome changes what physicists can reasonably believe. A discovery would reveal a new connection between electron and muon identities. A stronger null result would show that the separation between those families remains reliable at an even finer level. The measurement does not need a dramatic flash. It needs the correct electron, the correct positron, the correct timing, and enough repeated atoms to distinguish an impossible-looking event from an ordinary accident. Muonium began as a surprising combination of matter and antimatter that could survive because its constituents were not direct partners. The possibility of antimuonium asks whether that protection is only part of the story. Perhaps the atom can preserve its total charge while exchanging every particle role inside it. Perhaps lepton identity is less permanent than it appears, or perhaps the conversion is so deeply suppressed that even the next generation of instruments will hear nothing. That silence would not leave the atom without purpose. The mass, spin, spectrum, decay, and possible conversion of muonium all test different parts of the same physical framework. Taken together, they turn a temporary two-particle atom into a survey of the rules beneath ordinary matter, which brings us to the larger question of what this tiny system may reveal when all of its measurements are considered side by side. Taken together, the measurements of muonium do more than describe an unusual atom. They let physicists compare some of the most successful ideas in modern science with an object that nature does not normally leave lying around. Muonium has only two constituents, but those constituents bring several major questions into the same experiment. Why does the muon exist? Why is it so much heavier than the electron? Do the two particles follow exactly the same interaction rules? Are the known forces the only ones acting between them? Can matter and antimatter identities change? Does gravity respond normally to an atom whose mass comes mainly from an antimatter particle? Muonium will not answer all of these questions with a single measurement. Physics is rarely that considerate. What it provides is a collection of precise tests in which different parts of the theory can be examined separately and then compared. One experiment measures an energy interval. Another measures a magnetic interaction. Another searches for a forbidden conversion. A future experiment may try to observe the atom falling under gravity. When the results are placed together, they test whether the same description remains consistent from one situation to the next. The first major question concerns quantum electrodynamics, the theory that describes interactions between charged particles and light. This theory has passed many demanding tests, but success does not make further testing unnecessary. A theory can agree with measurements in one system, while an overlooked effect appears in another. Muonium gives researchers a system made from an electron and a positive muon, with no proton or neutron inside it. That removes the uncertain internal structure of an atomic nucleus and allows the electromagnetic interaction between two leptons to be studied directly. This makes the atom particularly useful for testing bound state quantum electrodynamics. The phrase bound state matters because describing two particles held together is more difficult than describing a single particle moving freely. The electron and positive muon continually interact. Both move around their shared center of mass. Their spins affect each other. Their surrounding quantum fields contribute small corrections. The positive muon recoils much more than a proton would because it is considerably lighter. A calculation must include all of these effects at the precision reached by the experiment. The largest contribution gives the basic atomic structure. Smaller contributions account for relativity, magnetic interactions, recoil, and fluctuations of quantum fields. Still smaller contributions involve more complicated intermediate processes. Each improvement in experimental precision forces the calculation to include another layer. Muonium is especially sensitive to recoil effects because the positive muon is only a little more than 200 times heavier than the electron. That is still a large mass difference, but it is much smaller than the difference between an electron and a proton. The central particle cannot be treated as a motionless point. Its movement leaves a measurable mark on the atomic spectrum. This allows muonium to test parts of bound state theory that are less visible in hydrogen. In hydrogen, some recoil effects are smaller, while uncertainties related to proton structure become important. In muonium, nuclear structure is absent and recoil is enhanced. The atom changes the balance of the calculation, giving researchers a different view of the same electromagnetic laws. The measurements performed so far agree with quantum electrodynamics. That agreement is not a reason to lose interest. It tells physicists that any missing effect must be smaller than the current experimental and theoretical uncertainty. When the accuracy improves, that permitted space becomes narrower. The ground state hyperfine splitting is one of the strongest tests. It measures the energy difference created by the magnetic interaction between the electron spin and the positive muon spin. The result depends on the muon magnetic moment, the relative masses of the two particles, and detailed quantum corrections. The Muonium spectroscopy experiment, using microwave collaboration at the Japan Proton Accelerator Research Complex, has measured this splitting with a pulsed muon beam. Its near-zero field result reached a precision of slightly better than 1 part in a million. Further work aims to improve that precision by using more intense beams, improved microwave methods, and detectors capable of handling a very high rate of positrons. A better measurement would provide a more accurate value for the muon magnetic moment and the mass ratio between the muon and the electron. Those quantities can then be used in other calculations. This creates an important consistency test. A value obtained from Muonium spectroscopy can be compared with values derived through other experiments. If the different methods do not agree after every known correction has been included, something in the physical description or one of the measurements is incomplete. The transition between the lowest atomic state and the first long-lived excited state offers another route. The Muonium laser spectroscopy experiment at the Paul Scherrer Institute aims to measure this transition with far greater accuracy than earlier work. The goal is to improve the previous precision by roughly 1,000-fold. That transition is strongly influenced by the muon to electron mass ratio. A more accurate frequency can therefore provide one of the best determinations of the muon mass. Combining it with improved hyperfine spectroscopy may also give a value of the Rydberg constant that does not depend on the finite size of a proton. The Rydberg constant helps set the scale of atomic spectra. It appears throughout the description of hydrogen-like atoms. Many of its most precise determinations use ordinary hydrogen, which means that proton structure must be included. Muonium offers an independent route with no proton present. Agreement between a Muonium-based value and values obtained from hydrogen or other atoms would show that atomic physics remains consistent across very different systems. A disagreement could point to an incorrect input constant, an incomplete calculation, an unnoticed experimental effect, or an unknown interaction. Scientists would have to investigate those possibilities in that order, rather than immediately announcing that reality had been replaced overnight. The Lamb shift and the fine structure of Muonium test another group of corrections. These energy separations arise partly because the simple picture of a charged particle moving in an electric field is not enough. The electron interacts with quantum fluctuations and with its own surrounding field. Relativistic behavior and recoil also contribute. A precision measurement of the Muonium Lamb shift reported in 2022 improved the earlier result by about an order of magnitude and agreed with the theoretical calculation. Because no nuclear size uncertainty was present, the comparison allowed researchers to place limits on possible unknown interactions between electrons and muons. It also allowed tests of proposed violations of fundamental space-time symmetries. Further measurements of fine structure could examine additional radiative and recoil corrections. Proposed techniques use separated microwave interaction regions, allowing the atom to encounter a controlled field, travel for a short interval, and then encounter another field. The interference between these interactions can produce a narrower and more precise signal than a single interaction region. The coming generation of more intense muon sources may make such experiments practical. A higher intensity beam produces more Muonium atoms, which improves statistical precision. It also creates engineering problems. Detectors must handle more events. Targets must release Muonium efficiently. Backgrounds increase. Timing systems must separate signals that arrive close together. More particles are useful only when the apparatus can still determine what each event means. A laboratory can become very busy without becoming more informative, a problem not limited to particle physics. A second enormous question is whether the electron and muon experience unknown forces. The standard model gives them the same basic electromagnetic and weak interaction rules, while allowing their masses and lifetimes to differ. It does not explain why the muon is much heavier than the electron, or why the particle families occur in 3 generations. Muonium places an electron and a muon in the same bound system. If an unknown particle creates an additional force between them, that force could alter the atomic energy levels. The shift might be extremely small, but precision spectroscopy is designed to notice small shifts. Different proposed particles would produce different patterns. A force that depends only on the positions of the particles may shift several transitions in one way. A force that depends on their spins may be especially visible in hyperfine measurements. A short-range force may affect states in which the electron is more likely to be close to the positive muon. A longer-range force may influence the atom differently. No confirmed extra force has appeared. Current agreement places limits on how strongly any proposed new particle may couple to the electron and muon. These limits complement searches at colliders and in particle decays. A collider attempts to produce a new particle directly. Muonium spectroscopy searches for the small influence that a new particle could have without being produced as a real object. A heavy intermediary may exist only within the quantum interaction for a very short time. Its effect could still shift an atomic frequency. This indirect method can reach conditions that are difficult for direct production. It does not replace high-energy experiments. The two approaches answer related questions from different directions. A collider asks whether enough energy can create the particle. A precision atom asks whether the particle leaves a measurable influence on known matter. Muonium can also test whether the laws of physics depend on the direction, speed, or orientation of the laboratory. Modern particle theory is built on Lorentz symmetry, which says that the fundamental laws retain the appropriate form for observers moving at constant speeds and for experiments oriented in different directions. If this symmetry was slightly violated, an atomic transition could change as Earth rotates. The laboratory would gradually point in different directions relative to distant space. A frequency measured in the morning might differ slightly from the frequency measured later, not because the equipment warmed up, but because the atom responded to a preferred direction in the universe. The practical difficulty is that equipment really does warm up. Magnetic fields drift, gas pressure changes, laser systems move slightly, electronics respond to temperature. Any search for a daily or directional signal must separate a fundamental effect from these much less exciting causes. Muonium Lamb shift and fine structure measurements have already been used to constrain certain forms of Lorentz and combined charge, reflection, and time symmetry violation in the Moon sector. Better measurements could tighten those constraints and test combinations that other experiments do not reach. The combined charge, reflection, and time symmetry is usually described as a fundamental requirement of ordinary quantum field theories that obey several basic assumptions. It connects particles with antiparticles and relates physical processes to transformed versions of themselves. Finding a genuine violation would require a major revision of the theoretical framework. Muonium contains an antimatter muon and a matter electron, making it useful for comparisons involving both particle types. Antimuonium would reverse those roles. Precise comparison of the two systems would be especially powerful, although producing and identifying antimuonium remains the central challenge. This leads back to charged lepton flavor. The standard model separates electrons and muons strongly enough that processes changing one into the other are expected to be far beyond current sensitivity when only known neutrino mixing is included. Muonium to antimuonium conversion would break that expected separation. The next generation muonium to antimuonium conversion experiment has been designed to improve the current sensitivity by more than 2 orders of magnitude. It aims to test conversion probabilities around 1 in 10 trillion. A discovery would show that a new interaction connects electron and muon identities. Such a result would not explain itself automatically. Physicists would need to determine whether the interaction involved a new heavy neutrino, a new Higgs-like particle, a particle carrying twice the usual unit of electric charge, or another mechanism. The conversion rate, spin dependence, and response to magnetic fields could help identify the possibilities. a failure to observe conversion would still matter. It would remove more of the allowed parameter space from theories that predict charged lepton flavor violation. Models proposed to explain neutrino masses, dark matter or other puzzles often produce several effects at once. A model that appears successful in one area may predict too much muonium conversion and therefore be ruled out. Muonium is also connected to the wider study of muon behavior. Experiments search for a muon decaying into an electron and a photon, a muon decaying into 3 charged electrons, and a muon changing into an electron near a nucleus. These processes test different forms of the same general question. Can the muon and electron families transform into each other more easily than known physics permits? No single search covers every possible new interaction. Muonium conversion may be especially sensitive to a model that produces only a weak signal in ordinary muon decay. Ordinary decay searches may be stronger for another model. Combining all of them prevents an unknown interaction from hiding behind the limitations of one experimental design. Another question concerns the magnetic behavior of the muon. The muon acts like a tiny magnet, and its magnetic moment receives contributions from every particle and field that can influence it through quantum processes. Measurements of the free muon magnetic anomaly have reached extraordinary precision. The interpretation of those measurements depends on equally precise theoretical calculations, including difficult contributions from strongly interacting particles. Muonium does not remove those theoretical challenges, but it supplies independent information about the muon mass and magnetic moment. Better values of these inputs strengthen comparisons across muon physics. The atom can also test proposed new physics explanations that affect both muon magnetism and electron-muon interactions. If a new particle is introduced to alter the muon magnetic moment, it may also shift the Lamb spectrum or hyperfine structure of muonium. Spectroscopy can then restrict the particle's possible mass and interaction strength. This cross-checking is essential. A proposed particle should not be allowed to solve one discrepancy while quietly contradicting 5 established measurements. The same theory must survive everywhere it applies. Gravity offers a different kind of test. Muonium is electrically neutral and consists entirely of leptons. Most of its mass comes from the positive muon, which is an antimatter particle from the second generation. This makes it unlike ordinary test masses, whose mass comes mainly from protons and neutrons. General relativity predicts that muonium should fall downward like other objects. The atom's composition should not provide an exception. Anti-hydrogen experiments have already observed behavior consistent with gravitational attraction toward Earth, and have ruled out simple upward acceleration of equal strength for anti-hydrogen. Muonium would not repeat exactly the same test. Antihydrogen contains an antiproton and a positron, while muonium contains a positive muon and an electron. Antihydrogen is entirely antimatter and its mass is dominated by a composite hadronic particle. Muonium is a mixed matter and antimatter atom, is entirely leptonic, and has most of its mass in an elementary antimuon. A muonium gravity measurement could therefore test whether gravity behaves normally, for second-generation particles and for a system without quarks. It could also constrain speculative forces that depend on particle composition, rather than total mass alone. The proposed method uses atom interferometry. A slow horizontal beam of muonium would pass through a sequence of extremely fine gratings. The wave nature of the atoms would produce an interference pattern. Gravity would shift that pattern by a minute amount during the short flight. The difficulty is severe because muonium lives for only a few millionths of a second. It does not have time to fall far. The expected displacement is smaller than an atom, requiring exceptional control of alignment, vibration, temperature, and the muonium beam. A successful experiment would not be expected to show that muonium falls upward. Current theory and the existing evidence strongly favour ordinary downward gravity. The value would come from testing that expectation in a new type of system. Fundamental principles become trustworthy because they survive many different tests, not because they sound reasonable. Muonium may also contribute to chemistry and materials science. When it enters a solid, it behaves as an extremely light form of hydrogen. Its spin reveals local magnetic fields, electron distributions, and chemical reactions. It can show where hydrogen-like particles become trapped, how quickly they move, and how they interact with defects. These applications do not usually address antimatter directly, but they reveal how quantum motion changes with mass. Muonium is far lighter than hydrogen, so tunneling and vibrational effects can become much stronger. Comparing muonium reactions with hydrogen and deuterium reactions tests theories of chemical dynamics under an unusually large change of mass. This work connects fundamental particle physics with the behavior of real materials. The positive muon begins in an accelerator, becomes part of an exotic atom, reacts like a light hydrogen nucleus, and then reports its magnetic history through a decay positron. Few laboratory probes have a career with that much variety packed into 2/millionths of a second. There remains the broad question of why nature contains the muon at all. The electron is stable and builds atoms. The muon has the same electric charge and spin but is much heavier and decays quickly. The tau repeats the pattern at an even greater mass. The standard model describes these particles accurately, but does not explain why there are 3 generations or why their masses have the values they do. Muonium cannot provide a complete explanation merely by existing. It gives physicists a controlled way to compare the first and second generations. Every agreement supports the rule that electrons and muons differ mainly in mass and stability, while sharing the expected interactions. Every improved limit makes it harder for an alternative theory to introduce differences without being detected. A confirmed discrepancy would be more important than the small size of the atom suggests. An unexplained transition shift could indicate a new force. A directional change could challenge Lorentz symmetry. Conversion into anti-muonium could reveal charged lepton flavor violation. An unexpected gravitational response could challenge the equivalence principle or suggest a composition-dependent force. None of these discoveries is guaranteed. The most likely near-term outcome is a series of measurements that agree with the standard model more accurately than before. That may sound less exciting than finding a new particle, but it is how the boundaries of knowledge are established. Each agreement tells theorists where new ideas cannot operate strongly. Each limit reduces the number of possible explanations for the unanswered questions. Precision physics advances by making uncertainty smaller and then asking what still fits inside it. Muonium is useful because its theoretical description is unusually clean, its experimental signals are identifiable, and its ingredients connect several areas of physics. It is simple enough to calculate and strange enough to test rules that ordinary atoms cannot reach. The atom began with a positive muon slowing inside matter and capturing an electron. It resembled hydrogen without containing a proton. It survived matter and antimatter sharing the same bound state because its particles were not direct annihilation partners. It responded to microwaves and lasers before the muon decayed. Its decay positron allowed researchers to reconstruct what happened during a life too brief for human senses to notice. Now its role is clearer. Muonium is not important because it is large, stable, or common. It is important because its simplicity makes small effect visible. It places an electron beside an antimuon and asks whether every known rule still works. So far, those rules have worked. The measured spectrum agrees with quantum electrodynamics. No conversion into antimuonium has been confirmed. No new force has revealed itself. The positive muon continues to decay with the expected behavior, and the atom disappears almost as soon as it is made. The experiments continue because the questions remain. Why are there several lepton generations? Are their identities absolutely separate? Do unknown particles interact with electrons and muons? Are space-time symmetries exact? Can atomic constants be determined consistently without nuclear structure? Does gravity treat a purely leptonic, partly antimatter atom exactly as expected? Muonium gives each question a measurable form, a laser frequency, a microwave resonance, a positron direction, a missing event, a charge reverse decay, or a tiny displacement under gravity can become evidence. The equipment may be large, but the final test takes place inside one temporary atom. By the time the detectors record the positron, that atom is already gone. Another muon then arrives, another electron may be captured, and the measurement begins again. From billions of these brief repetitions, physicists build a clearer account of particles that cannot be seen directly, and forces that may be weaker than anything yet detected. That is what Muonium may reveal about reality. Not a single dramatic answer delivered all at once, but a precise comparison between what the theory predicts and what nature repeatedly does. For an atom that survives only a few millionths of a second, it gives science a remarkable amount of time to ask.